How does a quiet, shining star transform into a vast red giant? What hidden forces guide a star's graceful aging and final glow? Why do even dying stars leave behind such enduring beauty? In the quiet of a starlit night, far from the city's glow, the sky becomes a calm ocean of darkness, dotted with light. Countless stars shimmer gently overhead, each one a distant sun shining across the emptiness. Among these twinkling beacons are not just living stars in their prime, but also the subtle ghosts of stars long departed. These faint points of light are easy to overlook, yet they are the universe's quiet keepers of secrets, the embers of suns that once blazed brilliantly and have since entered a peaceful afterlife. Imagine lying back and gazing upward. The night air is cool and still. Above you, a soft band of the Milky Way arcs across the heavens, a mist of innumerable stars. Somewhere in that haze, hidden to our eyes, a tiny white star glows with the leftover warmth of a life now past. It's no larger than a planet, but it weighs as much as an entire sun. Nearby, perhaps in the remnants of a long-ago cosmic cataclysm, an even stranger object spins silently. A neutron star, the dense core left after a giant star's fiery death. They shine softly, or pulse faintly, like distant lanterns left glowing after the cosmic festival has ended. These are white dwarfs and neutron stars, the universe's dead remnants. Though their fires of fusion have gone out, they remain, quietly glowing or gently pulsing in the dark. Each one holds within it the history of a star that lived and died, preserving in its tiny form the memory of that star's journey. They are ancient stellar embers scattered across the galaxy, enduring long after the bright flames of youth have faded away. In the silence of space, they keep watch over the night, enduring and unassuming. Let us take a slow and gentle journey to understand how these mysterious remnants come to be. We will drift through time and space, tracing the life of a star from its humble beginnings to its final, quiet state. As we wander among nebulae and dying suns, we'll uncover how the ordinary warmth of a shining star gives way to the ghostly glow of a white dwarf, or to the hidden heartbeat of a neutron star. With a calm and wondering mind, we will explore how the delicate balance in a star's core eventually fails, how a giant star can shed its glowing layers like petals, and what remains in the aftermath. Through this journey, the cosmos will reveal how endings can be gradual and gentle, or sudden and profound, and how even in their ending, stars leave behind something beautiful, a quiet light or a subtle pulse that persists in the darkness for eons. In this peaceful exploration, every step will unfold slowly. Feel the vastness around us as we begin, the immense calm of outer space, where millions of years pass like the ticking of a clock, and where stars live out their lives in a grand, slow dance. Our voyage starts with a single star's birth and life, to set the stage for the transformations that follow. We'll move at a relaxed pace, as if floating through a great story that the universe whispers to those patient enough to listen. The night sky above holds its quiet keepers. Let us meet them gently, one chapter of their story at a time. Our story begins with a simple cloud of gas and dust, drifting silently in the darkness of space. In some forgotten corner of a galaxy, far from any bright lights, a faint glimmer of starlight falls on swirls of cosmic dust. The cloud is cold and dark, composed mostly of hydrogen, the most basic element, the stuff of which stars are made. For ages, this cloud floats undisturbed, a soft haze in the starlight. But slowly, over countless years, gravity begins to draw the wisps of gas inward. The cloud gathers and contracts, gently at first, then more insistently. Deep in its center, density and pressure quietly build. What was once a diffuse haze grows denser, warmer, and brighter at the core. A fragile glow kindles there, a preview of the star that will be born. As this newborn star ignites, it is not with an explosion, but with a steady lighting of a cosmic hearth. The core grows hot enough for hydrogen atoms to begin fusing into helium, and in that moment, a true star is born. Light and heat stream outward, pushing back against gravity's inward pull. The star finds its balance. It emerges from its dusty cocoon and shines for the first time into the cosmic night. The surrounding gas and dust are gently swept away by the new star's light and winds, revealing a shining young sun where once there was only darkness. It's a quiet birth by cosmic standards. No loud bang or flash visible across the universe, just a slow, steady illumination that gradually strengthens. Now our star settles into life, burning peacefully in what astronomers call the main sequence. This is the long middle age of a star's life, a time of stability and calm. The star steadily fuses hydrogen in its core, producing a gentle, constant glow. From a distance, this sun appears unwavering and eternal. For billions of years it will shine, barely changing at all from one millennium to the next. Inside the core, trillions of hydrogen atoms, each second, join together to become helium, releasing energy that sustains the star's warmth. Yet these reactions occur in an orderly, self-regulating way. If the core gets slightly too hot and intense, it expands and cools a bit, slowing the fusion. If it cools too much, gravity pulls it tighter and heats it again. In this way, the star maintains a delicate equilibrium, a graceful dance between pressure and gravity, heat and weight, holding itself up in perfect poise. Under the tranquil light of such a star, planets can form and life may flourish. All the while, the star itself remains a steady beacon. One could live an entire lifetime under the light of a sun like this and notice no change at all. The star's changes are measured in the slow clock of the cosmos. 1,000,000 years is a brief chapter in its life, and 1,000,000,000 years passes like a subtle shift in its brightness. Our own sun, as an example, has burned for about 5 billion years, and has about 5 billion more to go in this gentle phase. It is a time of contentment for the star, a long and remarkably uneventful summer before the whispers of change begin to stir within its core. But even the most enduring fuel is not infinite. Deep inside the star, the supply of hydrogen slowly diminishes as it is transformed into helium ash. For eons, the star will not notice any difference. There is plenty of hydrogen left, and the balance holds. Eventually, though, the change will come. In the far future, after ages of shining peacefully, our ordinary sun will begin to face a new chapter. The core's store of hydrogen will thin, and the quiet balance that sustained the star for so long will start to shift. The star does not know it yet, but this tranquil period is not forever. A subtle turning point approaches, one that will lead our once steady sun into a final, transformative act of its life. For a star that has lived in balance for so long, the first signs of change are subtle. Deep in the core, the hydrogen fuel that sustained the star's shining heart is nearly spent. Helium, the ash of all those millions of years of fusion, has accumulated at the center. There comes a moment when there is simply not enough hydrogen left in the core to keep the fusion reactions going. In that quiet moment, the delicate truce between pressure and gravity begins to falter. The core, which had been held up by the energy of fusion, now starts to cool and loses pressure. Gravity, ever present and patient, seizes the opportunity. It pulls inward with relentless force, and with nothing in the core to counteract it, the core begins to shrink. As the core contracts under its own weight, something unexpected happens. It heats up even more. The dying embers of hydrogen in the core cannot reignite, but just around the core, in a shell of gas that still has hydrogen, the rising heat kindles new fusion. A thin shell of hydrogen surrounding the inert helium core suddenly becomes a hotbed of activity. Fusion resumes there, in a new layer, pouring energy into the star's outer regions. This new energy flowing from the shell pushes outward on the star's outer layers. The balance the star had known is gone, replaced by a new and less stable configuration. The core is now a dense ball of helium ash growing hotter, and around it, a burning shell fuses hydrogen furiously. The star's interior is changing rapidly, though from the outside these changes begin gradually. The star, which once shone steadily, now begins to respond to these deep internal shifts. Gravity has compressed the core to a smaller, denser state, and the energy from the shell-burning hydrogen starts to inflate the star's outer layers. The star as a whole cannot remain the same size or brightness it was during its long, calm youth. Slowly, almost imperceptibly at first, it begins to swell and brighten. The surface of the star cools as it expands, taking on a reddish hue even as the star's overall luminosity grows. To any civilizations on planets orbiting this star, the changes would still be slow, perhaps noticed only over many millennia. But in the life of the star, the tipping point has been reached. The chapter of steady middle age has ended, and a new chapter has begun. Gravity has gained the upper hand in the core, and the star must adapt to a new equilibrium. Soon, the star will transform into something vastly different from the gentle sun it once was, stepping into the next stage of its life with a grand, quiet expansion. The once modest star is now a giant, swollen to many times its original size. What was a sun-like beacon has bloomed into a vast, red-orange sphere of light. Its outer layers have drifted far from the core, expanding outward into a tenuous veil of gas. The star's surface, now cooler and reddish, glows with a softer light, even as the star's total brightness has greatly increased due to its enormous size. This is the red giant phase, a gentle giant of a star, luminous but cooler at the surface, and so large that it might engulf any nearby planets that once circled close. The transformation is dramatic in scale, yet it unfolds slowly and serenely over time, as though the star is taking a long, deep breath and stretching itself across the sky. Inside the giant, the structure of the star has changed completely. The core that was once dominated by hydrogen fusion is now a dense, hot ball of helium ash. Around that core, a shell of hydrogen is burning furiously, adding more helium to the core with every passing year. If the star is massive enough, there may even come a time when the core grows hot enough to ignite the helium itself. Then, for a while, helium atoms will fuse into carbon and oxygen in the core, creating a new source of energy. In stars much more massive than our Sun, this process continues. When helium is exhausted, carbon might ignite next, then oxygen, and so on, each new stage adding another shell to the star's interior. Such massive stars build up layers of fusion one atop another, like the concentric rings of a tree trunk recording its life. A hydrogen-burning shell on the outside feeds helium to a helium-burning shell beneath it, which feeds carbon in the core, and some stars go on to even heavier elements. In the heart of the largest giants, one can find an onion-like tapestry of layers, hydrogen fusing to helium in the outer shell, helium fusing to carbon a layer down, carbon to neon or oxygen still deeper, and so forth, all the way to iron at the innermost core for the very heaviest stars. Each shell glows with its own fusion fires, a nested set of burning rings hidden inside the star's bulk. For our moderate star, though, the story will not progress that far. A star like the Sun can manage to fuse helium into carbon and oxygen once its core becomes hot enough, but it will go no further. The carbon and oxygen produced in the core mark the end of fusion's road for such a star. It simply cannot squeeze or heat the core enough to ignite those heavier elements. Still, the period of helium fusion in the core grants the star a brief reprieve, a second life, so to speak, where the core regains some stability. The star will shrink slightly from its maximum size and settle for a time into a more stable state, quietly burning helium in its center and hydrogen in a shell. During this time, the red giant shines steadily once again, though it is a very different star from the one it was in its main sequence youth. Eventually, however, the helium too will run out. Then the core will once more be left with nothing to burn, and gravity will tug at it yet again. The star will expand for a second time, often even larger than before, entering what's known as the asymptotic giant branch, a late stage of pulsations and gentle instability. It is a beautiful but final bloom for the star. In these advanced giant stages, the star's outer atmosphere becomes extremely delicate. The outer layers are so far from the core's gravity that they are only loosely held. Even a slight disturbance can send gas drifting off into space. The star becomes somewhat unstable, pulsating in and out like a slow, rhythmic breathing. With each gentle pulsation, or with the stellar breeze pushing outward, the star sheds some of its mass. Layers of gas peel away and float outward, creating expanding shells of material around the star. These layers form a sort of cosmic veil, a nebula that grows with time, illuminated by the star's light. In the far future, an observer might see a glowing shell or ring of gas surrounding the star, the result of the star softly unveiling itself, layer by layer. The star is effectively casting off its outer garments, revealing more of its inner core with each shedding. What remains at the center is a shrinking, heating core, still buried under a thinning envelope of gas, for now. This process is not violent and explosive, but gentle and gradual. The star, in its old age, appears to be calmly sloughing off the outer parts of itself that it can no longer hold. The term for the glowing cloud that can result is a planetary nebula, a serene, ethereal shell of gas, often formed by dying stars like these. Through a telescope, such nebulae appear as delicate rings or ghostly bubbles of light, beautiful testaments to a star's final gift to the cosmos. Each one is an announcement that a transformation is nearing completion. At the heart of those expanding shells lies the star's core, increasingly exposed. The soft unveiling is nearly over. Soon, all that will remain is the bare stellar heart itself, laid open to the dark of space, ready to begin its next existence as a new kind of star. At last, the moment arrives when the star's outer layers are almost entirely shed. What remains at the center is the exposed core of the star, a small, brilliant ember where once a great bloated giant stood. This core is incredibly hot and glowing white blue with stored heat. It is tiny in size, perhaps only as large as our Earth, or even smaller, yet it contains roughly half the mass that the star had back when it was a full, shining sun. All the thermonuclear fuel is spent. No fusion fires burn in this core any longer. It is composed mostly of the ash of the star's earlier nuclear burning, primarily carbon and oxygen, forged from helium during the red giant's final acts. This dense little sphere of carbon and oxygen is the stellar heart left behind, and it now begins its new life as a white dwarf. To an outside observer, a white dwarf shines with a steady but fading light. At the moment of its birth, when the core is first laid bare, it is extremely hot and luminous, though its light comes from residual heat rather than ongoing fusion. The fresh white dwarf may glow at tens of thousands of degrees at its surface, making it appear bluish white. It pours out ultraviolet rays that cause the surrounding nebula of cast-off gas to fluoresce in beautiful colours. Indeed, for a few thousand years, the expanding shell of gas is lit up by the core's brilliance, creating a planetary nebula that can be seen across space as a ghostly ring or cloud. During this time, the white dwarf at the centre is like a cosmic lighthouse shining on the fog of its own making. Gradually, the expelled nebula drifts farther away and thins out, no longer catching the core's light. The once giant star is now nothing more than a tiny, naked core cooling in the darkness. All that remains of the star's former glory is this compact orb of degenerate matter, holding on to the memory of its past within its atomic structure. We call it degenerate, not in a common sense of the word, but in a scientific sense. The matter is in an exotic state, governed by quantum rules, squeezed to a density so high that a spoonful of it would outweigh a mountain. This dense core doesn't collapse further because a new kind of pressure has taken over, one that does not rely on heat or fusion. It's as if the star's heart has become a diamond-like crystal of carbon and oxygen, supported against gravity by the principles of quantum physics themselves. This remaining core, this white dwarf, is extraordinarily small and faint compared to the star it once was. Yet it is still very massive and energetic internally. Imagine a sun's worth of mass packed into an object the size of a planet. Gravity on its surface is hundreds of thousands of times stronger than on Earth. If we could stand on its surface, an impossible feat, we would weigh as much as an elephant with each step, and a tossed pebble would fall back down with ferocious speed. Everything about this core is extreme, except for its appearance. To the eye, once the nebula has faded, the white dwarf star would just look like a dim star, often too faint to see without a telescope. No longer surrounded by the glory of a nebula, and no longer bright like a main sequence star, it rests in quiet isolation. Yet in that quiet, the white dwarf holds the history of its star. Layered within it are the byproducts of all the fusion reactions that once took place in its progenitor's core. There is helium from ages of hydrogen burning, now settled in its outer regions. Deeper inside are carbon and oxygen from the helium burning phase. In some cases, traces of even heavier elements might be embedded in the mix, depending on the star's life. The white dwarf is like a time capsule, a record of the star's life written in the arrangement of its atoms. It's also incredibly stable now, held up by forces we'll soon delve into. For now, though, we recognize that what remains is essentially the stellar ash, compressed and glowing. The once mighty sun has become a white dwarf, a smouldering ember in the cosmic night, marking the end of one path of stellar evolution. Now we pause to consider the strange force that props up this tiny star. In an ordinary star, the weight of the overlying layers is balanced by the heat and pressure generated from its hot, burning core. But in a white dwarf, the core no longer burns. the heat is slowly ebbing away, and yet the star does not collapse under its own weight. What then holds it up? The answer lies in an invisible pressure born of the quantum world, a pressure that exists even when warmth and fusion are gone. This phenomenon is called electron degeneracy pressure. It is a resistance that does not come from heat, like the springiness of ordinary gas, but from the fundamental limits on how tightly matter can be squeezed together. Inside a white dwarf, atoms are packed unbelievably close. Under the immense gravity, the electrons that once orbited atomic nuclei are forced into a tight crowd. Electrons, by the laws of quantum physics, strongly resist being pressed into the same state or the same space. They obey the Pauli exclusion principle, which, simply put, means no two electrons can be in the exact same situation at the same time. As gravity tries to crush the star's core further, the electrons refuse to be squeezed into a smaller volume beyond a certain point. They generate a powerful pressure by their collective reluctance to be compressed. This electron degeneracy pressure is like an invisible spring woven through the fabric of the star's matter, pushing outward silently and tirelessly. What's striking about this pressure is that it does not depend on temperature. In normal gas, cooler temperatures mean lower pressure. The gas would contract if it cooled. But the degenerate electron gas inside a white dwarf is different. Even as the white dwarf radiates its heat away over eons, the electrons continue to hold the star up. They are already in the lowest energy states available, and it's the sheer quantum rule that keeps them from being pushed closer, not thermal agitation. In a way, the white dwarf is supported by a kind of perpetual tension, a whisper from the micro realm that counters the crushing weight of gravity. This allows the white dwarf to remain stable and intact, even as it becomes colder and dimmer over time. The term quantum hush poetically describes this state. Where once the roar of fusion held the star aloft, now there is a profound silence in the core. Yet within that silence, the star is held up by this quiet, subatomic chorus of electrons. No sound, no flame, just the gentle, inexhaustible resistance of matter's smallest components, locked in an embrace with gravity. This is pressure without warmth, a serene counterbalance that allows a dead star's heart to persist. In the dark heart of the white dwarf, gravity presses in and the electrons push back, and a delicate peace is reached. The star has no internal fire left, but it doesn't need one to support itself. The quantum laws ensure its structure can endure. This is a remarkable ending for a star. To find stability, not through ongoing burning, but through the physics of degeneracy. So long as the star's mass isn't too great, this electron degeneracy pressure will suffice to hold it up indefinitely. The white dwarf becomes a cosmic monument to the power of quantum rules, shining faintly as it slowly cools, yet structurally sound, an eternal ember sustained by a silent, invisible pressure. This delicate balance will persist until or unless something disturbs the star, or until the universe itself grows cold around it. In this quietly supported state, the white dwarf will continue its long fading journey, secure against collapse by the quantum grace that is electron degeneracy. Nature, it seems, has set a final limit to the serenity of the white dwarf state. There is a boundary, a tipping point, beyond which the quiet support of electron degeneracy can no longer hold up a star's core. This is a whispered boundary, not loudly announced in the cosmos, but firmly fixed by the laws of physics. In a sense, the electrons can only push back so much. If the core of a star contains too much mass, gravity's pull becomes too intense for even the quantum pressure of electrons to resist. the star's heart then cannot find peace as a white dwarf. The threshold is reached at roughly 1.5 times the mass of our Sun, give or take. Below this limit, a spent core can settle gently into a white dwarf, supported by the electron pressure we described. Above this limit, gravity will overwhelm the delicate balance, forcing the core to collapse further in dramatic fashion. For stars that began their lives moderately sized, like our Sun, and up to a few times more massive, the core left behind after shedding its layers typically stays under this critical mass. These stars end their lives as white dwarfs, stable in their diminutive form. But consider a star much more massive, one that lived fast and died young in a blaze of stellar fury. When such a star exhausts its fuel, its iron-rich core, the final ash in a massive star's life, may easily exceed that mass limit. Electron degeneracy pressure tries to hold the line as the core contracts, but at this whispered boundary, gravity triumphs. The electrons are forced into atomic nuclei, combining with protons to form neutrons, and the core collapses catastrophically in the blink of an eye. In that moment, a new kind of remnant is born from the violence, a neutron star, or if the star is extreme enough, even a black hole. Even a peaceful white dwarf can be pushed over this boundary under the right circumstances. If a white dwarf is orbited by a companion star, it might slowly steal matter from its neighbour, growing heavier over time. Often, before reaching that critical mass, the accumulating gas can ignite in a more controlled thermonuclear flash on the white dwarf's surface, an event called a nova. In a nova, the star suddenly brightens as it blows off the newly acquired layer of fuel in a brilliant but relatively gentle explosion, one that the white dwarf can survive to potentially repeat again if it continues to siphon material. As it approaches the critical mass, the pressure in its core skyrockets. One of two things can happen. The increasing weight might ignite runaway fusion in a last flash of life, detonating the white dwarf in a brilliant supernova that completely destroys it. Or, if the collapse happens before a fusion runaway, the white dwarf's core will implode and transform into a denser object, a neutron star, leaving behind an explosion as well. Either way, crossing this boundary means the end of the white dwarf as it was. The serene ember cannot remain intact beyond that point. This mass limit, often called the Chandrasekhar limit after the scientist who discovered it, is like a quiet threshold in the universe's design. It's the line between a gentle fade-out and a more explosive next chapter. When we gaze at the variety of stellar remnants, we realize this limit is why some dead stars are simple glowing embers, while heavier ones are crushed into exotic neutron stars, or even darker things. The whispered boundary tells us that not all stars get to rest in peace as white dwarfs. Some are compelled by their great weight to take the story further. In the grand tapestry of stellar life cycles, this threshold is a fork in the road. To one side lies the tranquil plateau of white dwarf existence. To the other, the path of collapse toward neutron stars and black holes. It is a softly spoken rule of the cosmos. Beyond a certain weight, a star's death cannot be so gentle. Now we have met the white dwarf, a small, steadfast lantern shining in the cosmic dark. These stellar remnants, though far dimmer than they were in their heyday, remain aglow with residual heat. Picture a single coal glowing in the ashes of a long extinguished fire. That is a white dwarf against the backdrop of space. It may not illuminate its surroundings as brilliantly as a true sun, but its presence is unmistakable to those who look closely, typically only about the size of Earth. Yet containing the mass of a star, a white dwarf is incredibly dense and serene. It shines with a pearly white or blue-white light when young. gradually mellowing to redder hues as it ages and cools. In the vast darkness between stars, these white dwarfs are like scattered embers, each one a quiet testament to a star that once was. If you were to observe a white dwarf up close, you would find it both familiar and alien. Its surface might appear featureless to the eye, a smooth, blindingly bright expanse of glowing plasma, giving little hint of the exotic quantum mechanics at play within. Yet you would also sense its incredible gravity and compactness. This tiny star might weigh as much as our sun, but your spaceship could circle it in minutes due to its small radius. Its light, though faint by star standards, is stable and unflickering, a constant glow that slowly diminishes over the eons. White dwarfs do not have the raging storms or flares of their youth. Most of their drama is long past, and now they simply radiate away their remaining warmth in peace. Throughout our galaxy, billions of these stellar lanterns likely dot the darkness. Most are solitary, the final quiet companions to the grander narrative of the Milky Way. Some lurk near other stars as companions themselves, dim understudies to still living suns. Our own sun will one day join their ranks, becoming a faint white dwarf drifting through the galactic night. It's humbling to imagine the night sky of the far future, dominated not by bright new stars, for star formation will slow, but by these ancient, fading cinders. They will serve as gentle nightlights in the universe's deepening twilight, each containing in its silence the memory of a star's lifetime. Though a white dwarf seems like a final, unchanging thing, there are still secrets and subtle changes unfolding in its depths. Over immense spans of time, the hot carbon and oxygen core will cool and crystallize, like a liquid turning into a solid, eventually becoming something akin to a giant cosmic diamond. This process releases additional energy, causing the star to twinkle just a bit longer as it solidifies inside. And long, long after, the white dwarf will cool to the point where it no longer emits visible light, becoming a black dwarf, an almost undetectable remnant, the ultimate fate of a star's core. But our universe is not yet old enough for any star to have reached that final state. For now, all white dwarfs remain as softly glowing reminders of the stars they once were. Our journey up to now has followed one path of stellar death, the quiet fading into a white dwarf. We've seen how an ordinary star lives out its years and gently transforms into a cosmic ember. But not all stars go so quietly into that good night. Some, the giants among them, end their lives in a far more tempestuous way and become even denser, more enigmatic objects. As we continue, we will explore the fate of those massive stars. For now, we linger a moment with the white dwarf, this lantern in the dark, appreciating its calm and endurance. In the silence of space, it shines on, a beacon of what was, and a bridge to the deeper mysteries that await us in the next chapter of our journey. The story of a white dwarf does not end the moment it is born from the husk of a red giant. In fact, that moment is just the beginning of a new, extraordinarily long chapter. After the planetary nebula has dispersed and the white dwarf stands alone, it begins a very slow process of fading. With no new source of energy, it simply radiates away the heat it has, like a warm stone gradually cooling in the night air. This cooling takes billions upon billions of years. At first, the white dwarf is blisteringly hot, shining with a bluish-white hue. Over time, as millennia turn into millions and then billions of years, its light dims and its color shifts from white to yellow, from yellow to orange, and eventually to a dull red. The star becomes a ruby ember, barely glowing to the eye, yet still warm inside. As the white dwarf cools, something remarkable happens deep within its heart. The carbon and oxygen that make up the core begin to change state. You can imagine the atoms inside slowing their vibrations as the temperature drops. When the core temperature falls enough, the carbon and oxygen atoms start arranging themselves into a rigid lattice structure, a crystal. It's as if the very heart of the star is freezing solid, turning into an immense diamond-like object in space. This crystallization doesn't happen suddenly. It unfolds over long epochs, quietly. As parts of the core crystallize, latent heat is released, much like freezing water releases heat, which for a time slows the cooling of the star. The white dwarf, in its old age, gains a brief second wind from this hidden phase change. It will shine a little longer than it would have otherwise, all because its core is turning to solid crystal. Astronomers have found evidence of this cosmic crystallization. By studying populations of white dwarfs, they noticed that some older white dwarfs were staying warmer than expected, as though an internal heat source were briefly keeping them from cooling further. We now understand that this is the energy released during crystallization of the core. In a sense, many white dwarfs carry a cosmic jewel inside them, the end state of carbon and oxygen compressed to incredible densities and cooled into crystalline form. One famous white dwarf, poetically nicknamed Lucy after a song about diamonds, is believed to be a gigantic diamond in the sky, the crystallized heart of an old star. This concept captures our imagination, a star turning into a gigantic gemstone, shining faintly with leftover energy. As eons pass, the white dwarf continues to cool. After perhaps tens of billions, or even 100 billion years, time far exceeding the current age of the universe, it will have radiated away virtually all its heat. When its surface temperature drops so low that it no longer emits significant visible light, the white dwarf will effectively become a black dwarf, a cold, dark sphere of carbon and oxygen lurking invisibly in space. No black dwarfs exist yet, because even the oldest white dwarfs in the universe are still cooling from the heat of their formation. The universe simply hasn't been around long enough for any to fully go dark. But in the distant future, long after our sun and the other stars we know have died, the galaxies will grow dim, lit mainly by the residual glow of white dwarfs turning into black dwarfs. These cold, dark remnants will be the final stage of the most common stars, a kind of cosmic coal left after the fire has gone out. Yet, even as a black dwarf, the material is still there. The mass, the gravity, the crystal lattice of what was once a star's heart. It will simply be a star that has become a quiet cinder, undetectable to human eyes, but still a piece of the universe's grand story. Imagining such an object stretches our sense of time to realms we can barely fathom. The white dwarf's slow fade into darkness is a serene epilogue to a star's existence, a process so gradual that it's almost like an eternal twilight. And through it all, from the hot white dwarf we see today to the cold black dwarf of far tomorrow, the star's essence persists in this incredibly dense form. In the dying of the light, it finds a different kind of immortality, not in shining brightly, but in lasting almost forever as a quiet, crystalline memory of a star. Not all stars can slip gently into the night. For the giants among them, a far more dramatic destiny awaits. Consider a star dozens of times more massive than our sun, one that has burned through its life at a breakneck pace, In the final stages of such a star's life, its core has been fused into iron, the heaviest element that can be made by normal fusion processes. Iron is like ash in a fire. Fusing it doesn't release energy, it consumes it. So once a massive star's core fills with iron, the star faces an impending crisis. There is no more fuel that can stave off gravity. In a fleeting moment, lasting less than a heartbeat on the cosmic scale, the balance that sustained the star collapses. Gravity crushes the iron core with unimaginable force. The core implodes, and temperatures and pressures skyrocket beyond anything the star had experienced before. At the very instant the core can be compressed no further, a remarkable rebound occurs. The core, which has now transformed into an ultra-dense ball of neutrons, stiffens suddenly. The infalling material bounces off this newly hardened core. In that rebound, a powerful shockwave is born. It careens outward through the star's interior, tearing apart the overlying layers. The star's outer regions are blown off in a titanic explosion, a supernova. For a brief time, the dying star outshines an entire galaxy. The explosion sends freshly forged elements, things like gold, silver, and uranium, hurtling into space, seeding the galaxy with material for future stars and planets. Yet amidst this tremendous violence, at the center of the blast, something new and very small is left behind. The core that collapsed has now become a neutron star. To witness a supernova from a safe distance is to behold one of nature's grandest fireworks. There is a sudden appearance of a new star where none was visible before, brightening over days to a brilliance that can rival the whole host of stars around it. Then, over weeks and months, it fades away, leaving behind an expanding cloud of gas, and if we could peer closer, a tiny, dense remnant at its heart. But from nearby, such an event would be anything but peaceful. The shockwave and intense radiation would obliterate any worlds that once orbited that star. Thankfully, these explosions are rare and usually far from Earth. And in their aftermath, they offer the cosmos a strange gift. A neutron star, the compact core that will live on for eons after the supernova's light has faded. For years and centuries after the explosion, the remnants of the star drift through space as an expanding nebula, a glowing cloud of stellar debris. This supernova remnant, as it is called, is ethereal and beautiful. Tendrils of gas and dust spreading outward, still energized by the blast and by radioactive elements forged in the explosion. Colors of red and green, blue and violet, invisible to human eyes but revealed by telescopes, weave through the cloud, a cosmic aurora born from destruction. At the center of this delicate nebula, the newborn neutron star resides, often hidden by the haze. It might be emitting rapid pulses or beams, if it's become a pulsar, or shining faintly in X-rays. A tiny beacon, surrounded by the aftermath of its former self. Over time, the nebula will expand and fade into the interstellar medium, dispersing the elements that will one day form new stars and planets. But the neutron star remains long after the visible wreckage has gone. A lone, small guardian, standing amid the silence that follows the cosmic storm. The formation of a neutron star is a kind of second birth, the violent end of a massive star, giving way to the quiet beginning of a new entity. Amid the nebula of stellar debris that the supernova leaves behind, the neutron star emerges as an incredibly small but massive child of the explosion. This newborn neutron star is extremely hot and may spin rapidly, powered by the conservation of the original star's rotation. In time, The expanding veil of supernova debris will thin and drift away, and what seemed like chaos will reveal a singular, stable point of light at the center, the neutron star itself. It is as if, from the immense noise and fury of the supernova, a pin drop of silence remains, the quiet, dense core, ready to begin its own long existence as a stellar remnant. A neutron star is one of the most extreme objects in the universe. Imagine something with more mass than our sun, but compressed into a sphere only about 20 kilometers across, roughly the size of a city. It is as if an entire star were squeezed into the span of a small island. The density of such an object is mind-boggling. A single teaspoon of neutron star material, if you could somehow scoop it up, would weigh billions of tons on Earth, about as much as a mountain. In fact, neutron stars are so dense that they are comparable to atomic nuclei, but on a macroscopic scale. They are essentially giant nuclei, made mostly of neutrons, held together by gravity. This incredible density means that the gravity at the surface of a neutron star is immensely strong, millions or even billions of times stronger than Earth's gravity. If you could stand on a neutron star, an impossible feat, a tall mountain that would be less than an inch high, crushed flat by gravity's pull. Even a fleeting thought of dropping a pebble on such a star becomes fantastical. It would hit the surface with the energy of an atomic bomb, due to the immense gravitational acceleration. How can matter be squeezed so tightly? The physics at work in a neutron star is an extension of the same quantum principles that support a white dwarf, but taken to an even more extreme. In a white dwarf, electrons provided the pressure that held gravity at bay. In a neutron star, the collapse during the supernova is so intense that electrons and protons in the core merge into neutrons. Now it is these neutrons, packed side by side with virtually no empty space between them, that generate a new form of degeneracy pressure. Neutron degeneracy pressure, along with repulsive nuclear forces between neutrons, halts the collapse and props up the star. It is a tenuous victory over gravity. Any additional mass would crush even this resistance, potentially creating a black hole. But for cores beneath that ultimate limit, around 2 or 3 times the mass of the Sun, a neutron star finds a stable existence. It's a curious thought that the same quantum rules that quietly govern atoms on Earth are responsible for holding up an entire star against collapse in one of the loudest cosmic arenas. The surface of a neutron star is unlike anything we experience in our daily world. Under its immense gravity, ordinary matter is flattened and forced into exotic forms. The crust of a neutron star might be a solid lattice of atomic nuclei, mostly iron, squeezed into a crystal-like structure and embedded in a sea of free electrons. Beneath that crust, pressures rise so high that atoms can no longer exist. They dissolve, and the matter transitions into a fluid of neutrons, along with some protons and electrons. Deeper still, in the core, the densities may be so extreme that even neutrons begin to break down into stranger components, such as quarks, or form superfluid states where they flow without friction. The truth is, the exact composition of a neutron star's deepest interior remains one of the great mysteries of astrophysics. We cannot recreate those conditions on Earth, so we infer what we can from theory and observations. What we do know is that whatever lies at the heart of a neutron star is compressed beyond the density of any material found naturally elsewhere, a hidden realm where matter itself is pushed to its limits. Despite all this exotic complexity, from the outside, a neutron star appears rather simple. A perfectly smooth, hot, and small sphere, likely with a bluish-white glow if visible to our eyes. When it is first born, its temperature can be tens of millions of degrees, and it emits mostly X-rays. Over time, it will cool, and its emissions will shift through ultraviolet and optical light, though it may take hundreds of thousands of years to become cool enough to shine only with the faint red glow of heat. Most neutron stars that we observe are detected not by visible light but by other means, for instance by the radio pulses of a pulsar, if the neutron star is oriented just so, or by X-rays, if it's accreting material from a companion star. If one were to pass nearby, though, its gravity would betray its presence. Neutron stars warp the space around them significantly. Light passing close to a neutron star can be bent, and clocks would tick more slowly in its gravitational grip compared to far away. In essence, a neutron star is a tiny, massive remnant that has changed the rules of matter and energy in its vicinity. Looking up at the night sky, you might never realize a neutron star is there. They are usually invisible to the naked eye, mere pinpoints, if anything at all, overshadowed by the stars they once were. But with an understanding of their nature, we realize that scattered among the familiar stars are these ghosts of stars past. Each neutron star is a silent monument to a star that died in brilliance. Small and unassuming as it might appear from afar, it contains a universe of strange physics on the inside. In the grand scheme, neutron stars are relatively few, since only rare, massive stars produce them. But their existence adds a chapter of wonder to the story of the cosmos. These dense spheres, spinning and sometimes pulsing, remind us that even after a star's violent death, nature finds a way to create something new, an object of stark simplicity and mind-bending complexity all at once. Some neutron stars announce their presence in a spectacularly subtle way, by flashing or pulsing at us with perfect regularity. These are the pulsars, rapidly spinning neutron stars that sweep beams of radiation through space like cosmic lighthouses. To understand why they pulse, imagine the neutron star as a rotating sphere with a powerful magnetic field. Charged particles are trapped by this magnetic field and accelerated near the star's magnetic poles, emitting focused beams of radio waves and sometimes X-rays or light. If the magnetic poles are not aligned with the star's axis of rotation, these beams swing around as the neutron star rotates, like the rotating lamp of a lighthouse on a dark shore. A distant observer sees a flash each time the beam swings past. When a pulsar's beam points toward Earth, we detect a burst of radio waves, a pulse. Many neutron stars spin incredibly fast. Some rotate dozens or hundreds of times each second. This means the pulses can be separated by mere fractions of a second, creating a rapid, steady rhythm. Discovered in 1967 by astronomers who at first half-jokingly nicknamed the signals LGM for little green men, pulsars have proven to be natural cosmic clocks. Their pulses are so precise that some rival atomic clocks in stability. The fastest pulsars, called millisecond pulsars, whirl hundreds of times per second, their beams sweeping by Earth like the ticking of an unimaginably swift metronome. To a radio telescope, a pulsar's signals arrive as a steady series of blips or beeps. To our imaginations, we can think of it as the heartbeat of a dead star, still beating long after the star's life has ended. It's a haunting and beautiful concept. Even in death, the star's core spins on, faithfully flashing its cosmic beacon. The effect of a pulsar in the sky would not be visible to our unaided eyes. Their visible light is usually far too faint, and their flashes too quick for human perception. But if we could exaggerate the view, say, speed up time, or magnify their brightness, we might see a tiny star blinking on and off with incredible regularity against the darkness. Some pulsars slow down very gradually over millions of years, their heartbeat easing as they age. Others, especially those in binary systems that accrete fresh energy from a companion, can spin up or maintain their speed for a very long time. In any case, when we contemplate pulsars, we might imagine a tiny distant pulse in the silence, a reminder that hidden in the darkness are spinning cores of once mighty stars, ticking away the cosmic time. A special class of neutron stars, called magnetars, deserves mention as well. Magnetars have magnetic fields thousands of times stronger than ordinary neutron stars, the most intense magnetic fields known in the universe. These magnetic titans rotate more slowly, perhaps once every few seconds, but their fields are so powerful that they can occasionally twist and crack the neutron star's crust, releasing sudden bursts of high-energy radiation. A magnetar flare is a brief, fierce event. In a fraction of a second, it can unleash more energy than our sun emits in many years. Thankfully, such outbursts are rare and usually happen far across the galaxy. Most of the time, even a magnetar would appear as a relatively quiet neutron star, its incredible magnetic potency invisible except through its subtle influence on surrounding space. Knowing they exist adds another layer of awe. As if neutron stars weren't extreme enough, nature sometimes pushes the envelope further with magnetars. They remind us that the cosmic zoo of stellar remnants holds more surprises than one might first suspect, each variation a testament to the richness of the universe's imagination. Throughout this exploration, we have considered solitary remnants of stars. But sometimes, even in their death, stars do not end up alone. In some corners of the galaxy, two stellar corpses can find themselves locked in an eternal dance. Imagine two neutron stars orbiting one another, the remnants of a binary pair of massive stars that lived and died together. After their supernovae, they remain as a bound duet, two city-sized spheres whirling around a common center. From a distance, their dance is quiet and dark. No bright light emanates from these dense stars as they circle each other in the void. Yet, as they spiral slowly inward over the eons, they stir the fabric of space-time itself, sending out gentle ripples known as gravitational waves. These waves are exceedingly faint, far beyond our senses, but they carry news of the dance to the rest of the universe. For millions of years, the two neutron stars orbit in a delicate balance, gradually drawing closer. Their motion quickens imperceptibly over time, a slow acceleration as gravity brings them together. We can picture this approach as a gradual tightening of their waltz. There is no sound in space, no friction to slow them down, only the emission of those subtle gravitational waves, which rob the system of a tiny bit of energy, causing the stars to inch nearer. As the eons pass, the orbital period shrinks from hours to minutes to mere seconds. In their final moments, those neutron stars are spinning around each other dozens of times each second, a last furious crescendo to their age-long dance. Then, in one fleeting instant, the dance comes to an end. The two neutron stars meet and merge in a final embrace. The merger is one of the most powerful events in the cosmos, briefly flaring with more light than entire galaxies. But from a great distance, one might only catch the whisper of it, a sharp burst of gravitational waves spreading out like concentric ripples on a cosmic pond. If one could somehow feel these waves passing by, it would be a faint stretching and squashing of space itself, lasting just a moment. This is the universe's silent fireworks. No noise, no bright spectacle to the naked eye, yet an immense release of energy in a form that slips quietly through the void. What remains after two neutron stars merge is often a single, heavier remnant. It could be a more massive neutron star, at least for a time, or perhaps it collapses further into a black hole, the darkest enigma of star death, an object of such gravity that not even light escapes. If a black hole is born, it is in a sense the final step in the continuum of remnants. Beyond the white dwarf's gentle glow and the neutron star's dense presence lies the utter darkness of a star that has completely fallen in on itself. But even that end has its own quiet tale to tell, through the gravitational echoes of its formation and the subtle imprint it leaves on its surroundings. The idea of two dead stars merging might sound violent, and indeed it is, but there is a certain serenity in viewing it from afar. Over most of their life together, those neutron stars simply orbited calmly in darkness, their presence betrayed only by those soft gravitational ripples. The cataclysmic finale, while extreme, lasts only an instant. What's left afterward is again silence, perhaps a rotating black hole, or an ultramassive neutron star, surrounded by the faint glow of matter that was flung out. In the grand timeline, the lengthy quiet of their inspiral and the quiet that follows the merger outweigh the brief flash of chaos. It is another reminder that in the cosmos, even the loudest events are bookended by tranquility. The gravitational waves from such mergers, now detectable with our sensitive instruments on Earth, bring us a gentle message from those distant dark events, a whisper from the universe that even in destruction, there is a kind of order and rhythm. These ripples in space-time arrive as the faintest tremors, telling the story of two dead stars that pirouetted into one. They allow us to hear the cosmos's silent catastrophes, giving us insight without ever disturbing the peace of our night sky. In their aftermath, a profound calm returns, and the merged remnant, be it neutron star or black hole, carries on in solitude as the universe quietly continues its eternal evolution. Not all neutron stars spend their lives in solitude. Some remain in binary systems, partnered with another star, and this can lead to a different kind of afterlife drama. Picture a neutron star and an ordinary companion star orbiting each other in a tight embrace. The neutron star's immense gravity can pull streams of gas away from its partner. As this gas spirals down onto the neutron star's surface, it forms a swirling accretion disk, a whirlpool of superheated material glowing in X-rays. These systems are known as X-ray binaries, and they are among the brightest X-ray sources in the sky. From Earth's perspective, we cannot see the neutron star or its disk with our eyes, but space telescopes reveal their energetic dance. The infalling gas crashes onto the neutron star's surface at incredible speeds, releasing bursts of high-energy light. Sometimes, if enough gas accumulates, it triggers a brief nuclear flash on the neutron star's surface, an X-ray burst, which causes the system to flicker intensely for a moment. After the burst, the neutron star returns to its steady X-ray glow as it gradually siphons more material from its companion. To an outside observer at optical wavelengths, an X-ray binary might appear as an ordinary star with a faint, invisible partner. Yet if we could see an X-ray light, we would witness a blinking, flickering beacon as the neutron star feeds on its companion's offerings. This process can continue for eons, as long as there is gas to fuel the disk. Eventually, the donor star may lose much of its mass, or the two stars may evolve and change their relationship in complex ways. But through it all, the neutron star persistently draws sustenance, a quiet vampire star illuminated by periodic flares, a reminder that even in the quiet death of a star, interactions with a neighbor can stir up new energy and activity. In the end, when the fuel from the companion is finally exhausted or the stars drift apart, the neutron star will return to a quieter state, carrying on alone once more in the cosmic night. The energetic X-ray flashes will subside, and it will cool and slow down over the millennia. It will remain as we often imagine such remnants, an almost invisibly small, dense cinder, spinning quietly amid the darkness, content again in solitude. In the vast tapestry of the night sky, the bright stars we see are only part of the story. Invisible to our eyes, scattered among them, are the remnants we have journeyed with tonight, the glowing white dwarfs and the mysterious neutron stars. These unassuming objects, tiny as planets or as cities, yet massive as suns, carry within them the history of once great stars. They are the quiet afterglow of stellar life, enduring long after the fiery brilliance of youth has faded. White dwarfs, like cosmic embers, radiate a gentle warmth for billions upon billions of years. Neutron stars, the dense cores of giants, sit in their solitude, sometimes sending out rhythmic pulses to remind the universe of their presence. Both are incredibly silent in their own way. Their tumultuous birth throes are over, and what remains is steady, subtle, and enduring. As our journey draws to a close, we reflect on the serene and slightly eerie beauty of these stellar corpses. It is awe-inspiring to think that the universe tucks away such marvels in the darkness, embers and pulses that hold the secret of how stars end. On a clear night, when you gaze up at the stars, consider that somewhere out there, a white dwarf might be casting off its last thin shreds of light, or a neutron star might be ticking softly like a celestial clock. We do not see them easily, but we know they are there, and their story adds depth to the darkness. There is a profound calm in understanding that even destruction in the cosmos leads to these quiet forms of persistence. The star that dies in a blaze can leave behind a beacon that steadily counts the ages. The star that gently fades can remain as a warm ember through the eons. In this way, nothing in the universe truly ends abruptly. There are always transitions, remnants that bridge past and future. White dwarfs and neutron stars remind us that endings can be both beautiful and strange. They are the universe's way of turning loss into a different kind of existence, one that can last far longer than the star's shining life. So, as we end our gentle exploration, we find comfort in the idea that the night is watched over by these quiet keepers. The cosmos is not a place of emptiness, even in death, but rather a gallery of transformed beings, stars that have shed their bright outer layers to live on in hushed simplicity. In the silence of space, the white dwarf glows softly, and the neutron star whispers in pulses. Together, they are the enduring chorus of a universe that never truly sleeps. The soft lights and faint heartbeats that carry on the legacy of stars, lighting the darkness in the most unassuming yet profound ways. In knowing them, we have listened to a cosmic lullaby, one that speaks of change, endurance, and the quiet resilience at the end of a star's life. And now, under the gentle sky, we can drift into our own quiet night, feeling just a bit more connected to the calm, mysterious universe above. In the aftermath of a dying star's final breath, a tiny core remains behind, shining alone in the darkness. It is a cosmic paradox. A star so small it could sit comfortably between our planet's horizons, yet so heavy it rivals the sun in mass. This dense remnant glows a fierce white, a last echo of the brilliance that once came from its larger self. To an observer from afar, it might appear only as a faint pinprick of light, but up close, its surface blazes with intense heat, casting a stark glare into the surrounding night. This is a white dwarf, the shrunken heart of a star that has exhausted its fuel. Here, more mass does not mean more size. In fact, the more weight this stellar corpse carries, the smaller it becomes. It defies the common sense of everyday objects. Add matter to a normal star, and it swells larger, yet add matter to a white dwarf, and it shrinks tighter. This strange mass-radius dance is dictated by the dwarf's internal physics. Gravity crushes the star inward, but the star does not collapse outright. Instead, a quantum pressure from the star's own electrons holds it up, a delicate balance between the relentless squeeze of gravity and an invisible, subatomic force pushing outward. The result of this balance is astonishing density. Imagine taking something as massive as our Sun and compressing it to the size of Earth. That is the reality of a typical white dwarf. In such a compact world, a single teaspoon of its material would weigh as much as an elephant here on Earth. In silence and darkness, atoms are pressed so close together that their normal structure breaks down, merging into an exotic state of matter. The core becomes a packed sea of particles, with electrons roaming freely in a cloud that provides the outward push to resist further collapse. It is as if the star's very essence has been squeezed into a crystal of almost unimaginable weight and solidity. This extreme density gives the white dwarf a gravitational grip of incredible strength. Standing on its surface, if one could survive there, would be impossible. The pull of gravity is hundreds of thousands of times stronger than on Earth. A human would be crushed instantly under their own weight, amplified unimaginably. Even a bit of loose dust or gas cannot float lightly. Everything is pulled tight against the surface. Light itself struggles to escape the star's hold. Every photon leaving the surface must expend extra energy to climb away from the gravity, making the light just a touch less energetic when it finally departs. To us, that light appears ever so slightly redder, a subtle fingerprint of the star's mighty gravitational field. For all its gravity and density, a white dwarf shines in a quiet and enduring way. No new fusion fire burns in its heart. The tremendous heat it emits is merely leftover energy from a former stellar life, slowly radiating away. Its brilliance is stark but fading, a bright ember rather than a roaring flame. As it lights the darkness, it gradually cools over eons, like a hot coal left to glow and then dim. The surface temperature at birth can exceed 100,000 degrees, white and blue hot, and over billions of years it will gradually lose that feverish heat. Even as it cools and dims, its mass remains, locked in that tiny sphere by gravity's grip. More massive white dwarfs compress themselves ever tighter to hold up that extra weight. A relatively lightweight white dwarf might be somewhat larger, perhaps comparable to Earth or slightly bigger, while a truly heavy white dwarf could be significantly smaller, on the order of only 3/4 of Earth's diameter, or even less. This inversion, that the heavier star is the smaller, is a peculiar truth of these remnants. It is a consequence of gravity's deepening well. The heavier the star, the more intensely gravity pulls inward, and the more the star must contract and densify to support itself. All the while, the star remains remarkably stable, suspended between collapse and expansion in a lasting equilibrium. In their heyday, these stars once shone as normal suns, but now they are reduced to a city-sized sphere of degenerate matter. Every physical intuition fails on their surfaces. If you were to drop an object from just a few meters above a white dwarf's surface. It would slam into the ground at tremendous speed, accelerated by the enormous gravitational pull in an instant. Even molecules in the star's wispy atmosphere feel that pull. Heavier elements sink rapidly out of sight, leaving only a thin veil of the lightest gases at the exterior. Everything about the white dwarf speaks of compression and intensity. Small, heavy, bright, and bound by gravity. Yet for all its intensity, the white dwarf is calm and silent, hanging in space with no external sign of the tremendous forces within. It does not roar with the ferocity of a living star. It simply glows, a quiet beacon of resilience. Gravity's invisible hand has bound this star in an iron embrace, and the star responds by shining softly with its stored heat. We are left with an object at the limits of matter's endurance, a sphere where adding more weight only squeezes it smaller and harder, up to a limit beyond which even this exotic state cannot hold. Within this dense, bright shell lies the story of a star's lifetime, compressed into an object the size of a planet. These unusual properties made white dwarfs difficult to discover for many years. In fact, the first white dwarf was detected only indirectly. The bright star Sirius was observed to wobble from the pull of an unseen companion. When that companion, later named Sirius B, was finally observed through a telescope in the early 20th century, astronomers realized it was astonishingly dense and hot. A cosmic ember weighing as much as the Sun, but no larger than the Earth. Sirius B became the first confirmation that nature could forge such extraordinary stellar corpses. To put it differently, if we placed a white dwarf next to an ordinary star like our Sun, it would look like a tiny white-hot pearl alongside a bloated bonfire. The pearl is minute but blindingly hot, containing in its compact form nearly the mass of that huge star beside it. The contrast is breathtaking. Size and brightness do not tell the whole story of what mass and density lie within. As we contemplate this tiny titan, one might wonder what secrets lie inside such a dense star. Beneath the blinding white glow of its surface, one cannot help but ask, what is this remnant truly made of? It is a natural question, given the star's strange nature. And the answers lead us deeper into its story. We must peer beneath the surface to uncover the composition of this stellar ghost. The answer lies in the ashes of nuclear fire, the elements forged in the star's previous life, now locked in a degenerate crystal. These are clues to the star's true nature, the quiet story told by what lies at its core. Deep within, the white dwarf preserves the products of its past fusion, a chemical record of its evolution. In a sense, the core's composition is a time capsule of the star that once was. Most of these stellar remnants are built from the ashes of helium fusion, chiefly carbon and oxygen. In the parent star's waning days, the core was a furnace where helium atoms merged, creating carbon, and in more massive cases, carbon fused further into oxygen. When the star could fuse no further and shed its outer layers, it left behind this carbon-oxygen core, now a white dwarf. This means that at the heart of a typical white dwarf lies a crystal rich with carbon and oxygen nuclei, essentially the burnt-out fuel of the star's prior life, now turned to cinders. These elements, forged in the star's prime, quietly reside in the dense core, holding a record of the star's history in their very presence. Not every white dwarf shares the same composition, and the differences speak volumes about their origins. Some white dwarfs are made mostly of helium. Such objects are comparatively rare and hint at an unusual life story. A helium-core white dwarf suggests a star that never ignited the full blaze of helium fusion to make carbon. Perhaps it was a smaller star that aged slowly, or one that had its outer envelope stripped away by a companion before it could grow into a red giant. Deprived of the chance to fuse helium into heavier elements, its core remained helium, which then became the final compact remnant. In the darkness now, that helium core persists, gradually cooling just like its carbon-oxygen cousins, an invisible testament to a life cut short or altered by the star's circumstances. On the other end of the scale are white dwarfs with cores of oxygen and neon, sometimes mixed with a bit of magnesium. These are the remnants of more massive stars that pushed the fires of fusion one step further. In a star, perhaps 8 or 9 times the sun's mass, the core grew hot enough to fuse carbon into heavier elements like neon and magnesium. This process, in the star's late life, created an especially dense core of exotic elements. Yet even those stars did not explode as supernovae. Instead, they sloughed off their outer layers and left behind a core that had nearly crossed the threshold of catastrophic collapse. The result is an ultramassive white dwarf made of oxygen and neon, a dense, hot ember that carries the story of a star almost too massive to end in quiet. These heavy white dwarfs are relatively uncommon, but they show astronomers that nature sometimes stops just short of a supernova, leaving a hushed remnant with a composition richer than its lighter peers. Each type of white dwarf composition is like a chapter from a stellar autobiography. A carbon-oxygen dwarf speaks of a sun-like star that lived out its life cycle through helium fusion and gently faded. A helium dwarf hints at an interrupted tale, a star that was changed by external forces or destined by its low mass to end before heavier elements could form. An oxygen neon dwarf murmurs of a giant that nearly met a violent fate, but instead ended in silence as a super-dense cinder. Though these objects all look similar from afar, tiny white or red points of light, slowly cooling, their internal makeup is a quiet archive of the star's personal history. Astronomers deduce these compositions through a combination of theory and observation. We cannot directly see into a white dwarf's core, but we understand from nuclear physics what elements should remain after certain fusion processes cease. Additionally, subtle clues sometimes emerge in the star's light. As a white dwarf cools and ages, convection or surface disturbances can dredge up traces of core material or heavy elements, revealing themselves in the spectrum, the rainbow fingerprint of starlight. In some white dwarfs, the atmosphere is found to contain a sprinkle of heavier elements like calcium or iron, suggesting that either those elements diffused upward or perhaps were deposited by asteroids and comets, falling onto the star. These spectral signatures give a peek into the composition below, confirming the presence of elements that theory predicts. Astronomers categorize white dwarfs by these spectral clues. The most common are designated type DA, showing strong hydrogen lines in their spectra, whereas type Db white dwarfs display chiefly helium lines. Others are classified as Do, Dc, Dz, and so on, depending on whether they show ionized helium, almost no lines at all, or detectable traces of heavier elements. Each spectral class paints a slightly different picture of the thin atmosphere's composition and history. For the most part, however, the core's secrets remain locked beneath a thin outer skin. The brilliant pinpoint of a white dwarf's light that we see is emitted from a slender atmosphere only a few hundred kilometers thick. This outer layer is often composed of the lightest elements, usually hydrogen, sometimes helium, forming a thin veil over the dense heart below. To an observer measuring the starlight, the white dwarf's composition appears deceptively simple, just hydrogen or helium gas at the surface. Yet behind that simple facade lies the true bulk of the star, the nuclear ash of a sun's life hidden from direct view. While the core composition speaks to the star's past, the outer layer that we actually observe holds clues of its own. That thin skin of hydrogen or helium at the surface is our window into the white dwarf's nature. Through the light it emits, and the spectral lines it imprints, it is in those delicate surface layers that we detect the characteristics which allow us to classify and study these stars. To truly appreciate a white dwarf's secrets, we must examine that tenuous atmosphere, its thin skin, and interpret the deep secrets encoded in its light. Beyond revealing composition, those spectral lines can whisper other information as well. Because a white dwarf's gravity is so intense, it subtly shifts these lines from where they would normally be. As light escapes the star's gravitational well, it loses a tiny bit of energy. To us, that loss shows up as a slight reddening or stretching of the light's wavelength, a phenomenon known as gravitational redshift. Early in the 20th century, astronomers observed this effect in the spectrum of Sirius B, confirming the tremendous gravity packed into that small star and providing a triumphant test of Einstein's theories. As light struggles out of the star's deep gravitational well, we see its telltale change in color, a gentle tug toward the red end of the spectrum. It's a gentle, silent effect. The hydrogen or helium lines in the spectrum appear at slightly redder colors than they would in a laboratory on Earth. This gravitational redshift is a soft but telling clue woven into the starlight, evidence of the white dwarf's powerful gravitational pull on everything, even light itself. The width and shape of spectral lines also change with temperature and pressure. In a hot, young white dwarf, the lines may be broadened by the effects of high temperature and dense atmospheric pressure. As the star ages and cools, the lines sharpen and shift. By carefully analyzing these subtle details, scientists can infer how hot the surface of the white dwarf is, and by extension, how long it has likely been cooling since the star died. In this way, the delicate traces in the spectrum serve as a diagnostic tool. The star's atmosphere, thin as it is, carries the record of its thermal state. Occasionally, that thin skin is not perfectly pure hydrogen or helium. Some white dwarfs show faint lines of heavier elements, a bit of calcium, magnesium, iron, or other metals appearing in the spectrum. Given the intense gravity, such heavier atoms should quickly sink out of sight, so their presence is intriguing. These polluted atmospheres often mean the white dwarf has recently accreted material from outside, perhaps swallowing a stray comet or asteroid from a long-vanished planetary system. The debris, vaporized and mixed into the atmosphere, introduces heavier elements that momentarily leave their fingerprints in the spectrum before gravity drags them down into the depths. In this way, even a thin skin of a white dwarf can tell the story of cosmic litter, the remnants of planets or asteroids that once orbited the star, now fallen onto the stellar corpse. Thus, by reading the spectral lines, astronomers have even detected signs of rocky planetary material in the atmospheres of some white dwarfs, discovering the ashes of worlds mixed into the light of these dead suns. Through it all, the atmosphere remains a calm, silent blanket, only a tiny fraction of the white dwarf's total mass, but vitally important for interpreting the star. The photons that reach our telescopes originate from this thin layer, carrying with them the imprint of all these effects: composition, temperature, gravity, and any recent cosmic meals the star might have had. In the quiet lines and subtle shifts of that starlight, we decode the white dwarf's properties. It reminds us that even in death, a star can undergo metamorphosis, not with a bang, but with a quiet reorganization of its innermost matter. The term white dwarf might conjure an image of a simple, inert cinder, but inside these objects, there can be a slow, beautiful transformation as they cool. Having gleaned so much from the white dwarf's feathery outer layers, we can now step back and consider the passage of time for these stellar remnants. The thin atmosphere radiates the star's heat into space, slowly cooling the white dwarf. Over eons, what do these cooling embers become? To answer this, we look at white dwarfs as cosmic clocks, tracking the fading of their light from the bright start to the final darkness, a journey that unfolds over billions upon billions of years. When a white dwarf is first born, the exposed core of a star that has shed its outer layers, it is blisteringly hot. Its surface may exceed 100,000 degrees, and its interior is even hotter. In these early moments of its new life as a white dwarf, the star loses heat rapidly through an invisible channel. Deep in the core, at temperatures and densities beyond imagining, a flurry of ghostly particles called neutrinos is produced. These neutrinos hardly ever interact with normal matter, so they slip away freely, carrying energy with them. It is as though the white dwarf is whispering away its heat into the void, a soft and silent cooling that we cannot see with our eyes. This neutrino cooling phase, though brief on cosmic timescales, is vital. In the first million years or so, it allows the white dwarf to dim and cool significantly without much visible change. The energy is simply carried off by these phantom particles streaming out from the heart of the star. As the white dwarf cools and its core temperature drops, neutrino production dwindles. The star then enters a new, much slower phase of its life, a long radiative cooling. Having lost the initial burst of heat through neutrinos, the white dwarf now relies on photons, ordinary light, to shed energy. This stage can last for billions upon billions of years. The white dwarf glows from its residual heat, radiating light into space and gradually fading. Its once fierce white-blue shine begins to soften. Over time, the star's colour shifts from brilliant white to yellow, to red as it cools, much like an iron pulled from a forge goes from white-hot to dull red as it loses heat. The decline is inexorable but slow, a prolonged winter of the star's life where warmth ebbs away at a glacial pace. Because there is no new source of energy within a white dwarf, its cooling is a one-way journey. In principle, given enough time, the star would cool to the point where it no longer emits any visible light, becoming a black dwarf, a cold, dark sphere of ash floating invisibly in space. However, the universe is still too young for any white dwarf to have cooled that far. Our cosmos, at roughly 13 to 14 billion years old, hasn't existed long enough for even the oldest white dwarfs to completely fade to black. The oldest white dwarfs observed are still glowing, albeit very faintly, with temperatures of a few thousand degrees. They are like dying coals that haven't yet fully lost their heat. Their presence tells us that the universe has been around long enough to cool these stellar embers to that extent, but not longer. In essence, black dwarfs remain a theoretical future state. None exist yet, because not enough time has passed since the universe began. One day, trillions of years hence, the universe will be littered with these black dwarfs, cold, lightless spheres that once were stars. They will mark the final end of starlight, the quiet tombstones of suns. This predictable cooling behavior makes white dwarfs into natural clocks. Every white dwarf, by its temperature and brightness, carries an imprint of its age since it became a stellar remnant. A hot, bright white dwarf is a young one, fresh from the furnace of a star's collapse. A cooler, reddish, and faint white dwarf is an ancient one, that has been quietly radiating away its energy for billions of years. By constructing theoretical models of how white dwarfs cool over time, astronomers can estimate the age of a white dwarf from its temperature and luminosity, much like one might estimate how long a coal has been fading by how much glow it has left. On a grander scale, ensembles of white dwarfs become powerful tools for gauging the ages of stellar populations. Consider a cluster of stars, or the galactic halo. Within those populations, many stars have lived out their lives and become white dwarfs. The collection of white dwarfs in a group will show a range of temperatures, some younger, some older. If the cluster is very old, it will contain some white dwarfs that are extremely cool and dim, the ones that have been cooling since the cluster's earliest days. There will also be a cutoff in brightness. Beyond a certain faintness, no white dwarfs are found, simply because there hasn't been enough time for any to cool further. This faintest white dwarf serves as a timestamp for the cluster's age. By observing the dimmest white dwarfs present, astronomers can infer that the cluster must be at least as old as the time required for a white dwarf to cool to that level. In young clusters, only relatively bright white dwarfs exist, indicating less time has passed since those stars lived and died. In globular clusters, some of the oldest gatherings of stars, the population of white dwarfs provides a record of the cluster's history, each faint star a marker of epochs long past. For instance, one globular cluster's faintest white dwarfs have been measured to be so cool that they imply the cluster's age is over 12 billion years, nearly as old as the galaxy itself. The agreement between white dwarf cooling ages and other age indicators gives us confidence in our understanding of how the galaxy and its stars have evolved over billions of years. In this way, white dwarfs act as timepieces for the galaxy. They allow us to probe the passage of cosmic time. For example, the halo of our Milky Way contains very old stars, and among them we find ancient white dwarfs that are barely glowing. Measuring their temperatures and luminosities, scientists estimate that these relic stars have ages approaching the age of the galaxy itself. In one ancient globular cluster, the faintest white dwarfs detected indicate an age of over 12 billion years for the cluster, nearly as old as the Milky Way. Such measurements establish an observational limit on the maximum possible age of the universe. The cooling of a white dwarf is a slow fading of light, but not an entirely steady one. There are subtle inflection points in the process. At certain temperatures, as the core cools, changes in the internal structure can release extra energy or alter the cooling rate. One such milestone occurs when the dense matter in the core begins to crystallize, a transition from a fluid-like state to a more solid crystal lattice. This phase change can temporarily slow the cooling, as energy is released in the formation of the crystal structure. It's as if the star, in solidifying its heart, gives off a last bit of warmth, a slight pause in the long decline of its brightness. During the crystallization phase, we witness the white dwarf's cooling curve take a slight detour, a pause in the decline of brightness, once the latent heat of crystallization has been released. The cooling resumes its long march toward darkness, but the fact that these stars crystallize at all is a testament to the strange conditions inside them. Densities and pressures so high that matter behaves first like a quantum gas, and then, at lower energy, like a forming solid. In the quiet of the white dwarf's core, structure and symmetry arise out of what was once a chaotic plasma. The star grows older, and in growing older, it becomes more orderly at heart, even as it fades. This silent formation of crystals does not manifest in the white dwarf's appearance to our eyes. The star from outside still looks like a dim point of light. Only by studying many white dwarfs could astronomers uncover this hidden change. In 2019, astronomers analyzing thousands of white dwarfs in a space survey found an unusual pile-up of stars at certain colors and luminosities, a clear sign that their cooling had slowed. It was exactly what theory predicted for crystallization, providing direct proof that these stellar cores were freezing into vast cosmic diamonds. It reminds us that even in death, a star can undergo a final metamorphosis, not with a bang, but with a quiet reorganization of its innermost matter into crystalline form. It's astonishing to consider that in the final stages of a star's life, after all the tumult and fire have ceased, its very core becomes an enormous crystal. The raging furnace that once burned in its center has long gone out, replaced by a serene lattice of ions locked in place. It is as if the star's lifetime of energy has been memorialized in this silent, orderly structure. A white dwarf's transformation into a giant diamond at its heart is a quiet, beautiful epilogue to the story of a star. As the white dwarf's core freezes into a solid lattice, other aspects of the star remain locked in as well. Any magnetic field the star possesses becomes embedded in that crystallizing core, preserved like a fossil of the star's younger days. Long after the core has turned solid, the invisible magnetism lingers around the white dwarf, influencing its surroundings in subtle ways. In fact, many white dwarfs carry significant magnetic fields, and these fields too tell part of the star's story. Now that we have peered into the crystal heart of a white dwarf, we turn to the quiet pull of its magnetic field, the lingering force that these dead stars often carry, and the gentle mysteries it introduces into their tale. Long after a white dwarf has cooled and dimmed, it may still hold an invisible remnant of its former self, a magnetic field frozen into its dense core. When the star was young and vibrant, currents and convection in its interior could have generated magnetic fields. As the star collapsed into a white dwarf, those magnetic field lines were squeezed closer together, intensifying like the tightened loops of a spring. What remains is a field that can be tremendously strong, yet quietly maintained within the stellar remnant. In many white dwarfs, this magnetism endures for billions of years, etched into the degenerate matter as if written into stone. The white dwarf becomes a cosmic magnet, though one that we often only detect through subtle clues in its light. White dwarfs with magnetic fields can be discovered by the effect of that magnetism on their spectrum and light. The field can cause certain spectral lines to split or shift, a phenomenon known as the Zeeman effect. An astronomer examining the light from a white dwarf might notice that what should be a single spectral line has been broken into multiple components, a clear sign that a strong magnetic field permeates the star's atmosphere. In other cases, the star's light may be polarized, the magnetic field imparting a preferred direction to the light waves. These are quiet signals of a powerful magnet at work. Some white dwarfs have truly staggering magnetic strengths. While Earth's magnetic field is measured in fractions of a Gauss, a magnetic white dwarf's field can be millions of Gauss or more. Imagine a force millions of times stronger than Earth's magnetic pull, embedded in a star the size of our planet. The strongest white dwarf magnetic fields known reach hundreds of millions of Gauss, approaching the realm typically associated with neutron stars. Yet, unlike the dramatic pulsar beacons of neutron stars, a magnetic white dwarf usually shines placidly, its field a hidden presence revealed only through careful observation. These magnetic fields also influence the white dwarf's behavior and environment, albeit subtly. A strong magnetic field can channel the flow of charged particles around the star, shaping any nearby plasma into beams or curtains along magnetic lines. However, a solitary white dwarf in the emptiness of space might not show obvious magnetic phenomena. there's little material around it for the field to act upon. The star itself rotates, often much more slowly than a neutron star. Many white dwarfs spin at a leisurely pace, taking hours or even days for one rotation. Over time, as the star cooled and contracted from a red giant to a white dwarf, it likely shed a good deal of its angular momentum, perhaps through stellar winds or the ejection of its envelope. The result is that in their old age, these stellar remnants turn sedately. With such slow rotation, a magnetic white dwarf does not whip its field around rapidly in the way a pulsar does. Instead, its magnetism is a steady, fixed structure in space, more like a bar magnet quietly sitting, rather than a dynamo. If the white dwarf has a magnetic field that is tilted relative to its rotation axis, the star's slow spin might cause the field to sweep through space over each rotation. This could create periodic changes in the star's observed light, or polarization, as the magnetic geometry shifts from our perspective. In a sense, the star could act as a very gentle lighthouse, with the magnetic pole rotating into and out of view. However, any such signaling would be extremely faint and slow, far gentler than the sweeping beacon of a pulsar. Because white dwarfs rotate slowly, and their emission is not as tightly beamed as a pulsar's, these effects are subtle at best. Over long timescales, any misalignment between the magnetic field and the spin axis might even diminish, leading to a quiet alignment where the field and rotation synchronize. The white dwarf's magnetism then becomes a static fixture, calmly threading through space around the star. Thus, for most white dwarfs, the magnetic field and rotation eventually settle into a stable, unchanging configuration. It is when a magnetic white dwarf interacts with a companion star that its hidden power becomes more apparent. Should gas from a nearby companion fall toward the white dwarf, the magnetic field can dramatically influence how that accretion happens. Instead of swirling into a broad disk, the infalling material may be captured by the magnetic field and guided along its lines straight to the white dwarf's magnetic poles. As the gas streams down the field lines, it gains tremendous energy and crashes onto the surface near the poles, heating those regions to extreme temperatures. The result is a pair of hot spots at the magnetic poles, shining brilliantly in high-energy light. From a distance, we would see the white dwarf brighten periodically as these hot spots rotate in and out of view, assuming the poles are not continuously visible. These systems are sometimes called polar white dwarfs, named for the polar concentration of light, and they create what one might poetically think of as cosmic auroras. However, unlike the gentle auroral glow of Earth's skies, these polar lights are incredibly intense, releasing X-rays and ultraviolet light as matter violently slams into the star's surface. Still, despite this violence, the entire process is governed by the quiet guidance of magnetic fields, invisible lines directing matter in near silence through space, until it meets the stellar surface in a burst of energy. In the absence of a companion and accreting matter, a magnetic white dwarf's influence is more subtle, but no less real. Its magnetic field, though invisible, can affect any charged particles or cosmic rays passing nearby, and stands as a lasting imprint of the star's history. It is remarkable to think that a dead star, fading and cooling, can still wield such a force, shaping matter and light around it. The magnetic personality of a white dwarf adds yet another layer to the complexity of these objects. We have now seen how gravity, composition, temperature, crystallization, and magnetism all contribute to the story of a white dwarf. Yet the tale is not complete without considering the relationships these stellar remnants have with other stars. Many white dwarfs exist in binary systems, where their fates become intertwined with companions. In those close partnerships, white dwarfs can undergo new bursts of activity, drawing matter from their neighbours. In the next chapter of our journey, we will explore these paired lives, the gentle siphoning of material, the swirling disks of gas, and the quiet glow of accretion that can briefly revive these stellar corpses. In many star systems, a white dwarf is not alone in its final repose. It often orbits in tandem with another star, a pairing forged when both were young and maintained even after one has died into a dwarf. This companionship can profoundly affect the white dwarf's later life. If the other star is close enough, and especially if it begins to swell into a red giant, its outer gas can drift toward the compact dwarf. This transfer often begins as the larger star's atmosphere extends into the white dwarf's gravitational domain. A stream of gas is pulled off the bloated star and flows through the inner space between them. In effect, a delicate bridge of material forms, connecting the donor star to the white dwarf. Through this bridge, gas trickles steadily into the white dwarf's grasp, a stellar siphon that slowly drains the outer layers of one star to feed the other. The white dwarf's intense gravity pulls on the wisps of that gas, drawing them in. Bit by bit, year by year, the living star feeds its dead companion. It is not a violent process, but a slow transfusion, a gentle flow of matter from one star to the other, almost like water seeping from a leaking cup into a waiting vessel below. As this gas spirals down towards the white dwarf, it doesn't usually fall straight onto the surface. Both stars are orbiting their common center, and the transferred gas carries the motion of the star it came from. Instead of a direct plunge, the gas forms a swirling accretion disk encircling the white dwarf. If one could observe this binary system up close, the white dwarf itself might be difficult to pinpoint, lost in the brilliant whirl of the disk around it. The scene would resemble a tiny galaxy in miniature, a bright central source surrounded by a delicate luminous ring. This disk is a broad, flattened ring of material, glowing softly as it converts gravitational energy into heat. Friction and turbulence within the disk heat it to temperatures of tens of thousands of degrees or more, causing it to emit a faint bluish-white light, often rich in ultraviolet. In the darkness of space, such a disk might appear as a dim, hazy glow around the otherwise inconspicuous white dwarf. It is a quiet light, steady or gently flickering, a sign that the dead star is being fed with new material. Within the disk, gas gradually loses energy and angular momentum and drifts inward. Eventually, it reaches the inner edge of the disk and falls onto the white dwarf's surface. When this gas finally settles on the dwarf, it does so relatively gently, at least by cosmic standards, spreading out across the star's surface in a thin layer. The white dwarf, which shines only from its leftover heat, now gains an additional source of energy, the heat released by infalling matter. This can make the white dwarf appear a bit brighter than it would in isolation. In effect, the accretion process has revived the remnant star just a little, clothing it in a borrowed luminosity. The soft glow of accretion is often detectable in these systems, an extra hint of energy that reveals the transfer of mass in progress. The transfer of mass is not always perfectly steady. At times, the flow of gas can increase or decrease, causing the disk and the white dwarf to brighten or dim. Some accretion disks experience instabilities, sudden surges of luminosity known as dwarf novae, when portions of the disk heat up rapidly and then cool again. These are like hiccups in the otherwise smooth feeding process, momentarily making the system much brighter. But even these outbursts are modest compared to what can happen on the white dwarf's surface itself. For now, under a gentle rain of hydrogen or helium-rich gas, the white dwarf quietly accumulates a fresh layer of fuel. Gallons of star stuff spread across a sphere the size of Earth, building up a tenuous shell of new life atop the old core. Through this ongoing accretion, the two stars are bound in a kind of cosmic symbiosis. The donor star, often a bloated red giant, or perhaps a smaller star overflowing its Roche lobe, continuously loses mass, which the white dwarf gains. The white dwarf, in turn, may respond with subtle changes. A slight spin-up if the infalling material carries angular momentum, a gentle warming of its surface where the gas settles, or the occasional flicker of light from a disk instability. To observers, these binary systems are known as cataclysmic variables, and they often exhibit irregular light variations, hinting at the complex interactions unfolding in the darkness. In fact, some of the earliest recorded variable stars that mysteriously brightened and dimmed in the night sky, were later recognized as such interacting binaries. Their gentle flickers and occasional flares were the visual clues of a white dwarf quietly stealing and heating fresh fuel from a companion. In some systems, the white dwarf's magnetic field, if strong enough, can disrupt the disk and funnel gas directly to its poles, as we have seen, producing focused streams and hotspots of emission. In others, the disk extends all the way to the star's surface, where the gas finally lands after its long spiral journey. All the while, the white dwarf grows slowly more massive as it accretes, though the amounts are typically tiny on astronomical scales. The donor star, conversely, is gradually stripped of its outer layers. This delicate dance can persist for a very long time, until something changes. Perhaps the donor star exhausts its envelope, or the influx of matter triggers a dramatic reaction on the white dwarf's surface. We are approaching just such a turning point in our story. As the white dwarf gathers material, piling up hydrogen-rich gas on its surface, a silent tension is building. The conditions in that accumulated layer are growing extreme. Pressure rising, temperature climbing. Eventually, the calm accretion will set the stage for an explosive event. For a long period, the white dwarf's accretion goes on quietly, almost imperceptibly. The faint star and its companion may show subtle fluctuations, but nothing dramatic to a casual observer. Yet all the while, pressure is building in that stolen layer of fuel. And then, in an instant, the tranquility ends. Then, quite suddenly, the quiet star erupts. The accumulated layer of hydrogen on the white dwarf's surface ignites in a runaway thermonuclear flash. In a momentary burst, nuclear fusion races through this shell of gas, releasing a tremendous surge of energy. The white dwarf's brightness explodes upward, increasing by thousands or even tens of thousands of times. What was once a faint, unnoticed star can become visible as a new star in the sky, outshining its entire previous self for a short time. To ancient sky watchers, it would seem that a new star had been born where none was seen before, hence the name nova, Latin for new. Throughout history, sudden appearances of such stars were recorded with awe. Ancient astronomers in China, for instance, described guest stars that emerged and later vanished, very likely witnessing novae or even supernovae. They had no way to know that a long-dead star was briefly blazing back to life. In truth, it is not a birth, but a brief awakening of a long-dead star, a sudden and spectacular reminder of the fuel it has quietly gathered. This is a nova, the white dwarf's dramatic revival, powered by the fusion of fresh fuel on its surface. The energy of the blast blows the recently accreted gas out into space. A shell of hot, glowing material expands outward from the white dwarf, and long after the nova has faded, that shell continues spreading into space as a faint nebula of gas. It moves at thousands of kilometers per second, carrying away the star's excess. For days or weeks, the system shines with a brilliance far beyond its normal state. The light can be so intense that it rivals the brightest stars in the night for a time, before gradually fading. And yet, despite the magnitude of this explosion, there is no sound. In the vacuum of space, the great flash unfolds in eerie silence. If one could imagine standing nearby, a perilous prospect, they would witness an expanding fireball of stellar gas rushing outward without a single audible note, a silent fireworks display in the cosmic night. After the nova has run its course, the white dwarf remains. It has cast off its temporary shell of flame, but the core of the star is largely unchanged by the outburst. The white dwarf returns to its quiescent state, a bit lighter than before, having lost the mass of the blown-off gas, but otherwise ready to begin the process anew. In some systems, if the conditions are right, the cycle can repeat. Fresh gas accumulates again from the companion star, and decades or centuries later, another nova may flare. These are known as recurrent novae, where the same star awakens multiple times across history. Each nova is a fleeting event, a few weeks of brilliance triggered by years or centuries of quiet gathering. In the grand scale of stellar phenomena, a nova is an enormous event to behold, yet it is relatively gentle compared to the most extreme explosions the universe has to offer. The white dwarf survives its nova intact. It is a surface phenomenon, a kind of stellar skin shedding. But there are greater fires waiting in the life of some white dwarfs. For the white dwarf, a nova is a dramatic event, but not a final doom, more a temporary flare than a terminal explosion. If the star continues to amass matter over a much longer period, pushing its mass toward a critical threshold, around 1.4 times the mass of our Sun, a far more violent fate looms. This tipping point, called the Chandrasekhar limit, occurs when the white dwarf reaches roughly 1.4 times the Sun's mass, at which point electron degeneracy pressure can no longer support it. Beyond that threshold, the entire white dwarf can ignite in one colossal thermonuclear blaze, not just a surface layer, but the whole star. Such an explosion is a supernova, an event so luminous it can outshine galaxies, and so violent it can utterly destroy the white dwarf. A nova, then, is a prelude, a relatively small spark presaging a vastly greater conflagration. Our story now stands at this juncture of violence and transformation. We have seen a white dwarf, a dead star, briefly rejuvenated by the nova's light, only to fall back into silence. But the prospect of the greater fire, the supernova, beckons. And beyond the realm of white dwarfs lies the domain of other dead stars that face different destinies. Neutron stars, born from the explosive deaths of massive suns. As we move forward, we will witness these ultimate cosmic explosions and the exotic remnants they leave behind. The quiet remnants have had their say. Now the stage is set for the cataclysms that forge neutron stars and unleash energies on an almost unimaginable scale. The next chapter of our journey will delve into these extraordinary events as the faint spark of a nova gives way to the blinding light of a supernova, and with it comes the birth of an even stranger stellar remnant. In the darkness of space, a small star remnant drifts quietly around a companion. This star is a white dwarf, an Earth-sized ember left from a sun-like star's final sigh. It glows faintly with residual heat, a soft pinpoint of light in a vast night. Nothing stirs on its surface. No new fusion burns within. It appears to slumber in eternal silence, supported against collapse by a delicate balance deep inside. From a distance, It looks like a faint amber star, barely perceptible, quietly shining among the blackness. Yet the white dwarf's story is not quite finished. Nearby, its companion star swells in old age, extending a diffuse outer atmosphere. Some of this gas drifts away and falls into the white dwarf's grasp. A gentle stream of matter flows toward the dwarf, like a slow breeze delivering fuel to a waiting ember. The white dwarf's gravity pulls this gas in, quietly collecting it on the dwarf's surface, layer by delicate layer. For now, this transfer is gentle and continuous, giving no hint of the drama it will one day ignite. The white dwarf's companion is a swollen, elderly star, perhaps a red giant, breathing its outer layers into space. This aging star has expanded so much that its outer gas is only loosely held by gravity. At the point where the white dwarf's pull becomes stronger than the red giant's hold, a slow transfer begins. Gas from the giant star flows towards the white dwarf, drawn along invisible lines of gravity. What was once the red giant's outer atmosphere now becomes a tenuous bridge of material, drifting in the direction of the compact dwarf. As the gas draws closer to the white dwarf, it doesn't fall straight in. Instead, the incoming stream spirals around the dwarf, spreading into a broad, thin disk of orbiting material. This accretion disk swirls quietly, heated just enough to emit a faint glow, perhaps in soft ultraviolet light or weak X-rays that would be invisible to human eyes, but detectable to instruments. The disk is like a silken whirlpool of stardust encircling the white dwarf, gradually feeding it. Through this disk, matter trickles down onto the white dwarf's surface in an almost unceasing drizzle. The white dwarf itself, despite its small size, holds a tremendous amount of mass. It packs as much mass as the Sun into a sphere the size of Earth, or smaller. This makes its gravity incredibly strong near the surface. A pebble dropped on a white dwarf would slam into it at thousands of kilometers per hour. A teaspoon of its material would weigh tons under Earth's gravity. These facts remain hidden beneath the white dwarf's quiet exterior, but they set the stage for what will eventually happen deep inside. Time in this system drifts onward in silence. Over years and decades, the white dwarf's mass increases almost imperceptibly. There are no dramatic changes on any given day or even any given year, just the steady, slow accumulation of gas. The process is so gradual that an outside observer would see virtually no difference in the white dwarf's appearance for a very long time. Yet, with each gram of matter that settles onto the dwarf, the internal pressure inches upward. It is a patient path toward an inevitable threshold. Over many years, this gentle feeding continues, and the white dwarf slowly grows heavier, one fine dusting of matter at a time. Its core, made of carbon and oxygen left from the star's past life, is squeezed tighter and heated ever so slightly more. Normally, a living star would swell and cool to counter such heating, but this dead star's dense heart cannot expand or shed its heat, so the temperature quietly climbs, the pressure rises, and energy builds up in the silence. The stage is being silently set for a profound transformation. There is no visible change outside, just a silent gathering of conditions within. The white dwarf remains outwardly calm, shining as a tiny pale star as it always has. Yet deep inside, the temperature creeps toward a critical threshold. It is as if a hidden storm is brewing in the core, pressure mounting in secret. In the stillness of that dense center, carbon atoms are on the verge of fusing. At last, in a moment as unremarkable as any other, the flashpoint is reached. In that unremarkable instant, everything changes. A tiny region at the star's center suddenly ignites. Carbon fusion begins in that instant, releasing a surge of energy in the surrounding matter. Under ordinary conditions, a new burst of heat might be tempered by expansion or carried away. Here, however, the dense star offers no such relief. The rising heat cannot push the unyielding matter aside. Instead, it raises the temperature even further, causing more carbon to burn. The reaction feeds on itself, a quiet flame turning quickly into a runaway fire that will race through the star. There is no turning back. The quiet star is now committed to its fiery fate. In the heart of the white dwarf, this sudden flame is like a false dawn. What was once cold and dark at the core now glows with intense heat. The thermonuclear burning spreads outward, illuminating the dense inner layers in a wave of nuclear light. At first it expands relatively slowly, a burning front that creeps through the carbon-rich interior, like the rosy light of early morning across a sleeping landscape. The star's quiet core is now ablaze, the first light of an internal sunrise. For the star itself, this false dawn marks the beginning of the end. As the energy release intensifies, the nature of the burn changes. The flame that began as a slow spread grows more furious. Parts of the star's fuel ignite nearly all at once under the enormous pressure. A powerful blast wave forms, a true detonation, and it races outward through the star faster than sound. This is a more violent phase, like a blinding flash of daylight following the gentle dawn. In just seconds, the thermonuclear fire sweeps through every corner of the white dwarf. Billions of tons of carbon and oxygen are fused in an instant, releasing unimaginable energy. In the blink of an eye, the star is consumed from within. Inside the white dwarf, the growing fireball remains confined for a brief moment. All the furious energy of the thermonuclear burn is trapped under the star's outer layers, like steam building under a lid. When the pressure becomes overwhelming, the containment breaks. A powerful shockwave races outward from the core to the surface. In an instant, it blows the star's surface open, and the blaze that was hidden within bursts free. For all its violence, this entire event unfolds in eerie silence. In the vacuum of space, there is no air to carry sound. A supernova makes no roar or crackle that anyone could hear from a distance. Only the light and expanding gas reveal its fury. To an outside observer, watching from afar, the detonation would appear as a sudden bloom of light and a growing halo of debris. But no sound. It is a silent firestorm in the dark, witnessed by the universe in light rather than noise. Matter that once formed the star is now flung into space at incredible speeds. The debris rushes outward in all directions. In the first moments, it moves at thousands of kilometers per second, fast enough to cross the distance of Earth to the Moon in mere minutes. The star that was once a solid sphere is now an expanding fireball, a shell of gas racing into the surrounding void. From the inside out, the white dwarf has been torn apart, its material freed from centuries of confinement and sent flying into the cosmic night. Now gravity's hold is broken. The white dwarf, as an intact star, ceases to exist in this moment. The tremendous energy of the blast drives all of the star's matter outward. From core to surface, every layer is flung into space at incredible speed. In a breath of cosmic time, the star is completely unbound. Nothing remains of the quiet dwarf's former shape, only an expanding, glowing cloud of debris moving outward into the darkness. All that remains is an expanding cloud of incandescent gas, marking the spot where the star once lay. The energy released is almost unimaginable. For a brief period, the exploding star radiates more power than millions of ordinary suns combined. In fact, when such a supernova happens relatively nearby, it can become visible to the naked eye, even in the daytime sky. Historical records from the year 1006 AD describe a guest star so bright it cast shadows at night and was visible during daylight, likely a supernova of this kind within our Milky Way. Such events stunned early observers, who suddenly saw a new light rivaling the moon in brilliance. It is a reminder that these stellar catastrophes, though rare, can momentarily dominate the sky with their ferocity. For an observer far away, the first hint of this cosmic blast is a sudden brightening of a distant point of light. What was once an almost invisible star now becomes visible, then grows startlingly bright. Over days and weeks, the supernova rises to a peak brilliance. At its height, it shines with the luminosity of billions of suns. For a brief time, one small star's death outshines the entire galaxy that was its home. What had been a quiet, forgotten ember is now a beacon visible across vast cosmic distances. In that distant galaxy, a long-dead star announces its end with a brilliant farewell. Astronomers have learned to use these brilliant stellar deaths as cosmic measuring tools. If you know how bright a light truly is, you can tell how far away it is by how dim it appears. These thermonuclear supernovae are so uniformly luminous at their peak that scientists consider them standard candles. Much like knowing the wattage of a distant lighthouse allows sailors to gauge their distance from shore, knowing the true brightness of a supernova allows astronomers to gauge the distance to its host galaxy. Each such explosion becomes a marker, a luminous signpost in the dark, indicating how far its light has traveled across space. It serves as a cosmic yardstick, allowing us to map the depths of space. Picture an astronomer in a quiet observatory, capturing the light of one of these distant supernovae. In the telescope's image, the host galaxy is a tiny smudge of light, and within it, a new pinpoint glows. The supernova outshining its entire galaxy. By carefully measuring how bright that point appears and comparing it to the known true brightness such supernovae reach, the astronomer can gauge the galaxy's distance. It is as if nature provided a standard bulb with a known wattage hanging in the depths of space, and by its apparent dimness we discern how far away it must be. With this cosmic light in hand, the once unfathomable gulf between galaxies becomes something we can measure. By comparing the true brightness of these supernovae to how faint they look from Earth, astronomers can determine their enormous distances. Some of these explosions are seen in galaxies billions of light years away. Because they shine so brilliantly and predictably, they serve as lighthouses on the cosmic scale. Each supernova's light carries not only a distance measurement, but also clues in its color and spectrum that reveal how fast its host galaxy is moving away, stretched out by the expansion of space. With these cosmic candles, scientists can chart the growth of the universe, measuring how space has expanded between us and the distant explosions. In this way, the dying embers of stars continue to enlighten us, connecting our knowledge across unimaginable distances. In the late 20th century, astronomers used these distant supernovae to make a profound discovery. They expected the pull of gravity to be slowing the expansion of the universe over time. Instead, the far-off supernova candles appeared dimmer than anticipated, implying they were more distant than expected under a slowing expansion. This was a startling result. It meant that the expansion of the universe has been speeding up. Space itself is stretching faster and faster, a mysterious acceleration that defied expectations. This astonishing result sent shockwaves through the scientific community. For a time, scientists struggled to believe what the supernova data was telling them. Could something have made the distant explosions look dimmer, like cosmic dust blocking the light? They analyzed and eliminated such possibilities one by one. The conclusion remained: the supernovae were genuinely farther than expected. Over subsequent years, more and more of these standard candles were observed, all pointing to the same conclusion. The evidence became overwhelming that an unknown force is at work. What began as a surprising faintness in distant starlight transformed into the discovery that reshaped our understanding of the universe. Today, dark energy is a central component of cosmology, inferred directly from the patient measurement of these exploding stars. To explain this cosmic acceleration, scientists propose the existence of a repulsive force or energy inherent to space itself. They call it dark energy. Dark because its nature is unknown and invisible. It acts like an anti-gravity, pushing galaxies apart more and more as time goes on. The discovery of this accelerating expansion through supernova measurements revealed how even in a star's violent demise, there are secrets about the universe's fate. In the gentle glow of a dying white dwarf, we found evidence that the cosmos will continue to expand ever more rapidly, guided by an enigmatic influence we are only beginning to understand, an enigma unveiled by the quiet demise of distant stars. The fact that a dying white dwarf can serve as a lighthouse across billions of light years is a profound cosmic irony. In extinguishing itself, the star illuminates the universe at large. These standard candles have extended our cosmic map to unprecedented scales. And in doing so, they delivered one of the greatest surprises in astronomy: that the universe is not only expanding, but doing so at an ever-increasing pace. The brilliance of those distant supernovae unveiled the influence of a mysterious dark energy that pervades the cosmos. In their final blaze, these tiny dead stars revealed a truth about the universe's fate, a revelation hidden in plain sight, written in the light of their explosions. The brilliant explosion fades after its peak, but the story of the stars remains, is only beginning. After the initial flash, the white dwarf's debris continues to rush outward into space, forming an expanding shell of hot gas and dust. This is the supernova's ash, the transformed elements forged in the thermonuclear fire. Immediately after the blast, much of it is radioactive nickel and cobalt, freshly minted from the star's carbon and oxygen. As weeks and months pass, these unstable atoms decay into iron and other elements, releasing energy that keeps the ejector aglow, even as the initial fireball begins to cool. The once brilliant supernova becomes a fading nebula of cooling ashes, drifting silently through the void. If one could watch the aftermath of such an explosion up close, it would be a breathtaking sight. Initially, the expanding shell is searingly hot and bright, a sphere of stellar debris glowing blue-white from its own heat. As it grows and cools, the glow fades from blinding blue to soft red. Delicate tendrils and filaments form as the blast wave plows into the surrounding space, sculpting the gas. The debris cloud, once uniform, becomes a beautiful tangle of glowing ribbons, the torn shreds of the star mixing with interstellar gas. Over years and centuries, this nebulous shell quietly expands and dims, turning into a ghostly remnant visible only to sensitive telescopes. Even centuries later, the imprint of such an explosion can be seen as a ghostly cloud. In the late 16th century, observers on Earth were astonished by a new star that appeared suddenly in the night sky, a supernova blazing in our galaxy. Long after that temporary star faded from human sight, its residue persisted. Today, telescopes reveal a faint, expanding nebula of gas at the spot where the supernova was witnessed. Thin filaments of glowing material mark where the stellar ash is still racing outward, hundreds of years after the explosion. This ethereal remnant is a snapshot of the aftermath, a bubble of enriched gas growing and cooling over time. Even centuries later, the sky carries a faint trace of that ancient fire. These supernova remnants continue to evolve for millennia. Eventually, the expanding gases become so diffuse that they merge into the general interstellar medium, the thin gas filling the galaxy. The heavy elements from the explosion, now spread far and wide, will drift for millions of years. In time, that enriched gas may cool and contract to form new stars and planets. Thus, each white dwarf supernova seeds the cosmos with heavy elements. The iron in the core of a new planet, the calcium in distant mountains, even the iron flowing in our blood. All were once created in supernovae like this. The death of a small star contributes to the materials for new worlds, continuing the cosmic cycle of matter from one generation of stars to the next. It is humbling to realize that our own existence is tied to such explosions. Elements like iron coursing through our blood, calcium in our bones, and many of the minerals of Earth were once forged in stellar furnaces and cast into space by supernovae. Long before the Sun and its planets formed, countless stars lived and died, enriching the cosmic clouds with heavy elements. Our solar system's birth material was seeded by those distant deaths. In this way, the violent end of one star becomes the life-giving ingredients for another. We are, quite literally, made of stardust. The ash of ancient stars lives on in us and around us. Not every supernova requires a normal star feeding a white dwarf. There is another path to cosmic fire, the merger of two white dwarfs, two stellar embers in orbit around each other. In rare binary systems, a pair of white dwarfs can be locked in a quiet, spiraling dance. They orbit their common center of mass for millions of years, slowly drawing closer together. With each orbit, they emit faint ripples in spacetime, gravitational waves, carrying away tiny bits of energy. Over a very long time, these two dead stars drift inward, until eventually their orbits tighten to the point of collision. As they spiral ever inward, time seems to slow, each orbit a prelude to their inevitable union. The merger sends subtle shudders through space-time itself. Ripples of gravity, gravitational waves, ripple outward from the coalescing stars, like concentric rings on a pond. These waves carry away energy and angular momentum, helping draw the dwarfs together in the first place. By the time of the final crash, a brief burst of stronger gravitational waves is released. They are too faint to notice on Earth with current technology. But one day, detectors might listen to the sky and catch the whisper of two white dwarfs merging in a distant galaxy. It would be a gentle cosmic chorus, the sound of space itself ringing from the union of two dead stars. Throughout their long spiral, the two white dwarfs remain inconspicuous in the darkness, but their final moments are tumultuous. As they draw extremely close, tidal forces can rip matter from one dwarf to the other. The smaller of the pair might begin to disintegrate, forming a transient bridge or disk of gas around the larger companion. In the last seconds before merger, the two cores plunge together. The collision happens in silence, a rapid melding of two ultra-dense spheres into one. In that instant, conditions decide whether they will quietly combine or unleash a thermonuclear fury. In a silent instant, two become one. When the two white dwarfs finally merge, the outcome depends on their combined mass and the details of their composition. If together, they exceed the critical mass that a white dwarf can support, The merger can ignite a runaway fusion just as surely as gradual accretion would. In an instant, both stars are consumed in a single, powerful supernova explosion. Two tiny embers that once orbited quietly are transformed into one brilliant fireball, leaving no remnant behind. The violence is over swiftly, and what remains is again an expanding shell of debris, similar to the one from a single white dwarf's explosion. Only this time it was two stars that provided the fuel for the cosmic blaze. However, not every merger leads to such a fiery end. Sometimes the two white dwarfs combine without triggering a complete explosion. If their total mass is below the instability threshold, the result may be a single, more massive white dwarf that survives the union. This new white dwarf might spin rapidly or possess an extremely strong magnetic field, helping to support its greater weight. It could be an unusual object, a survivor born from destruction, shining only faintly but with strange characteristics. In other cases, the merger might set off some fusion at the surface or in shells around the core, creating a temporary flare but not a full supernova. The two stars effectively melt into one, forming an odd, massive star that persists quietly, at least for a time. Astronomers continue to search for the telltale signs of past white dwarf mergers. In some cases, they have found stellar oddities that defy normal explanation. For instance, there are aging stars with almost no hydrogen in their atmospheres, composed mostly of carbon, a sign they may have formed from the merger of two helium white dwarfs that fused into a carbon-rich giant. Other stars are observed spinning unusually fast or sporting extremely strong magnetic fields, potentially the marks of a merged white dwarf that had to shed angular momentum or realign its internal structure. Each unusual survivor is like a cosmic fossil, offering clues about the merger events that created it. They are rare, but their existence hints at the diverse outcomes when two stellar embers become one. There is also the possibility of a merger leading to a different fate entirely. Not an explosion, but a collapse. If the merged white dwarf core reaches a critical density without igniting a blast, gravity may take over in another way. The star can implode, crushing itself into a neutron star without a spectacular supernova to announce the change. In such a case, two white dwarfs would have quietly combined and vanished as white dwarfs, replaced by a single ultra-dense neutron star. It is a silent, hidden outcome. Instead of a brilliant flash, the evidence of the merger would be a compact, dark remnant, an ember transformed into something even stranger. White dwarfs themselves, aside from their dramatic finales, serve as natural timepieces of the cosmos. Once formed, a white dwarf simply cools and fades like a dying ember. Without new energy sources, it grows dimmer and cooler in a very predictable way over billions of years. This makes each white dwarf a kind of stellar clock, steadily marking the passage of time since it was born. By measuring a white dwarf's temperature or brightness, scientists can estimate how long it has been cooling. The faintest, coolest white dwarfs are the oldest, their feeble glow a testament to eons spent radiating away their heat. In essence, they cool like predictable cosmic embers, marking the passage of time. In ancient star clusters scattered through our galaxy, these stellar clocks provide age estimates. Globular clusters, for example, are densely packed collections of old stars. Many of their most massive original stars died long ago, leaving behind white dwarfs that have been cooling ever since. Astronomers look at such a cluster and find the faintest white dwarfs still visible. The logic is simple. If a white dwarf has cooled to near invisibility, enough time must have passed for it to do so. By determining the cooling time needed to reach that faint glow, scientists infer the cluster's age. In some globular clusters, the coolest white dwarfs indicate ages of around 12 to 13 billion years, making these clusters among the oldest structures in the Milky Way. In practice, determining a cluster's age with white dwarfs is a bit like archaeology. Astronomers point powerful telescopes at an ancient cluster of stars, collecting the faint light of its residents. Amid the cluster's bright red giants and main sequence stars, they hunt for tiny, dim pinpoints, the coolest white dwarfs. It can take long observations to tease out these barely glowing embers from the background. When they succeed, they essentially uncover the cluster's oldest stellar fossils. By measuring how faint and red those oldest white dwarfs are, astronomers deduce how long they have been cooling, which translates into the cluster's lifetime. The result is like reading the diary of the cluster, a record of time spanning back to nearly the birth of the galaxy. Beyond individual clusters, the collective population of white dwarfs in the galaxy acts like a fossil record of star formation. Each white dwarf marks the death of a star that once shone. If we tally white dwarfs by their cooling ages, we can glimpse patterns in when their progenitor stars were born and died. For instance, a surge in the number of white dwarfs of a certain age suggests that many stars formed at the same time long ago. Thus, the very existence of white dwarfs at different stages provides a timeline of stellar life and death. Those stars eventually lived out their lives and became white dwarfs, creating a noticeable peak of remnants of that age. It's as though the galaxy's past rhythms are preserved in the distribution of these stellar remains. A peak in that distribution might correspond to an era of prolific star birth, while a gap could hint at a quiet lull in star formation. Thus, by studying white dwarfs of different ages, astronomers can reconstruct the tempo of star formation in our galaxy over billions of years. It is an intricate cosmic census of star birth and death. On a larger scale, the study of white dwarfs across our galaxy reveals the history of star formation itself. The number and ages of white dwarfs serve as data points, much like tree rings in an old oak. Some age groups of white dwarfs are more populous, indicating epochs when star birth surged and many stars were born together, all now leaving white dwarf remnants around the same time. Other age ranges show fewer white dwarfs, hinting at lulls in star formation. By piecing together these clues, scientists sketch a timeline of how our Milky Way lit up with stars across cosmic time. In the quiet glow of today's white dwarfs, we find echoes of those bygone eras of star birth. Looking far into the future, the cooling of white dwarfs points to an ultimate fate. After trillions of years, each white dwarf will become a black dwarf, a cold, dark sphere of degenerate matter with no remaining light. However, the universe is still too young for any black dwarfs to exist. Even the oldest white dwarfs still glow faintly. This means that by observing the least luminous white dwarfs today, we are also setting a lower limit on the age of the cosmos itself. The absence of any completely dark, ancient white dwarfs tells us that we live in a relatively young universe, still aglow with the fading light of its first stars. One can imagine the far future, when the universe has aged enough that white dwarfs cease to shine. Such an object, a black dwarf, would be practically invisible, a cold cinder in space. If an intrepid explorer in that distant epoch came upon one, they might only detect it by its gravitational tug, for it would emit no light. This is a fate awaiting every white dwarf, given time beyond reckoning. But at present, the universe is still young enough that even the oldest white dwarfs have not reached that final darkness. They glow on, faintly marking the deep cosmic time that has passed since their birth. Even with all we have learned, these cosmic fires hold lingering mysteries. Astronomers are still piecing together exactly how a white dwarf's final ignition is sparked in each case. For example, it remains uncertain which scenario is more common. Does a white dwarf usually explode after slowly stealing matter from a normal companion? Or do many of these supernovae come from two white dwarfs merging? Both paths likely occur, but the balance between them is not yet fully clear. The clues left behind are subtle. If a normal star companion were present, perhaps some trace of it might be seen in the aftermath, a leftover star, or telltale shells of gas. Yet such evidence has been hard to find. On the other hand, two white dwarfs merging leave little obvious sign either, aside from the lack of a companion. Thus, the origins of these explosions often lie in shadows, forcing scientists to infer what happened by indirect means. Another puzzle lies in the physics of the explosion itself. How does the flame spread inside the white dwarf? We know the burning likely starts in one spot and then engulfs the star, but the precise progression is complex. Does it begin as a slow deflagration, a subsonic flame, and then at some point turn into a supersonic detonation, as many models suggest? If so, what triggers that transition? Scientists continue to simulate these explosions in supercomputers, trying different conditions to see which can reproduce the observed brightness and spectra of real supernovae. The answers are not yet definitive. The star's death throes happen in a hidden, fraction of a second fury that we cannot observe directly, so our understanding must be pieced together from theory and the faint whispers encoded in the explosion's light. In the meantime, nature proceeds with its secret recipe, and each white dwarf that blows itself apart may follow a slightly different script within the same broad story. These supernovae themselves are not all identical. Most shine with a similar brightness and pattern, which is why they serve as standard candles. But a few have stood out as peculiar. Some appear slightly underpowered, fainter explosions that might indicate a partial detonation. In such cases, perhaps the white dwarf was only partially destroyed, leaving behind a small remnant. Indeed, astronomers have identified a handful of mini supernovae that didn't completely unbind the star. On the other extreme, some rare thermonuclear supernovae have been extraordinarily bright, hinting that the star that blew up may have been more massive than usual, or that two white dwarfs merged to create an overlarge blast. These outliers challenge our understanding and suggest a spectrum of possible outcomes for white dwarf explosions. Beyond the standard picture, each discovery of an unusual supernova adds another piece to the puzzle, reminding us how much we still have to learn. All these uncertainties are like shadows around our understanding, subtle hints that there is more to learn. Even the ultimate limit of a white dwarf raises questions. If one somehow grew past the tipping point without detonating, would it collapse in silence to form a neutron star instead? We have yet to witness such an event directly. It may be that some transitions happen quietly in the dark, never announcing themselves with a flash. In the end, each mystery is a reminder that the cosmos keeps some of its secrets. The fires of white dwarfs have taught us much, but they also lead us to the doorstep of deeper mysteries, the domain of neutron stars, where mass and pressure push matter beyond the familiar. Beyond a certain point, the gentle support that holds up a white dwarf can do no more. If the mass of a stellar remnant pushes past the threshold that electron pressure can uphold, the fabled Chandrasekhar limit, the nature of the collapse changes fundamentally. Instead of a runaway fire, gravity takes total command. Electrons and protons in the star's core are forced together, merging into neutrons. This is exactly what occurs in the core of a massive star at the end of its life. A sudden collapse that leaves behind a neutron star. The entire remnant implodes inward, shrinking rapidly and releasing a tremendous burst of energy as it does so. What emerges from this catastrophic compression is something new. A neutron star, an object even smaller and denser than a white dwarf, supported by the pressure of neutrons packed together. In mere seconds, a core that was the size of a city might collapse to the size of a small town, with density beyond imagination. Even a single teaspoon of neutron star material would outweigh the tallest mountains on Earth. This is another path of a star's end. Not a thermonuclear disruption, but a gravitational collapse that creates a different kind of stellar corpse. Thus, when the boundary of a white dwarf is crossed, a new chapter in the story of stellar remnants begins. The quiet embers of dead stars give way to something even more exotic. We stand at the threshold of neutron stars, mysterious cores of almost unimaginable density. Our journey now continues into the realm of these neutron stars, to explore the wonders and enigmas they hold. The voyage through the stellar afterlife continues onward, into deeper mysteries. Not every star can slip quietly into the night as a white dwarf. For those born with far greater mass, the finale is far more violent and transformative. Deep within such a star, an iron core swells, a heavy heart forged by eons of fusion. When that core grows too massive, the gentle outward pressure of physics falters. No more heat can be squeezed from fusion. In a silent instant, gravity takes command completely, and the core begins to fall inward without mercy. Within a fraction of a second, the star's core collapses in on itself. A sphere, once the size of a small planet, crumples swiftly to the scale of a city. Atoms are crushed and broken. Even the familiar boundaries between particles begin to blur. The heat soars to unimaginable levels as the collapse accelerates. Energetic gamma rays flood the core and start tearing iron nuclei apart, unmaking in moments what took billions of years to build. Stripped of structure, the core matter becomes a hot soup of subatomic particles, protons, neutrons, electrons, all rushing inward faster and faster. As densities climb higher, a remarkable transformation overtakes the plunging core. Electrons are slammed so tightly against atomic nuclei that they merge with protons. In this frenetic crush, protons and electrons cease to exist as separate particles, fusing into neutrons and releasing a flood of ghostly neutrinos. Those neutrinos, nearly massless and unbound, slip out of the core by the billions, carrying away the last whispers of the star's dying energy. For an instant, almost all light and life of the core is lost to that silent storm of neutrinos rushing outward into space. Still, the collapse continues, driving the core smaller and denser, until nature must find a new way to resist. The core material becomes so dense that it is no longer ordinary matter at all. Now it is nuclear matter, substance packed as tightly as the hearts of atoms themselves. In this extreme state, a new voice is finally heard. The quiet but unyielding pressure of neutrons. A neutron cannot be forced into the same space as another beyond a certain limit. A quantum refusal that suddenly stiffens the core. At roughly the density of an atomic nucleus, the collapsing core slams into this newfound wall of resistance. The infall slows, then stops, as though it has hit an invisible, unbreakable cushion deep inside. In that frozen moment, the core is saved from vanishing into a black hole by the collective might of neutron matter and the strong nuclear force binding it. But the rest of the star is still plummeting inward from above. All that infalling mass now crashes onto the halted core. Like a speeding wave hitting a cliff, the material rebounds. A powerful shockwave surges outward from the core's sudden standstill. The star that had been imploding just moments before is now being torn apart from within. The shock, energized by an enormous flood of escaping neutrinos, blasts through the layers of the star, ripping the outer envelope to shreds. It is a cosmic detonation, releasing almost unimaginable energy, a final outburst in the star's life. What follows is the titanic brilliance of a supernova, the star's last act of destruction and creation. In these few explosive seconds, matter that once formed the star's shining heart is hurled into space, seeding the galaxy with heavy elements that will one day form new stars and planets. The eruption's light can outshine an entire galaxy for weeks, but amid the fire and fury, something quietly remarkable is left behind. As the blast fades and the stellar debris races outward, the core remains, transformed and shrunken, but intact. The collapse that would not pause has given birth to an utterly different kind of star. The massive supergiant is gone, and in its place, sitting quietly in the wreckage of the supernova, a neutron star is born. Tiny, perhaps only 20 kilometers across, yet unimaginably dense, it contains more mass than the Sun, in a sphere the size of a city. This newborn neutron star is a silent, steadfast remnant, the last surviving heart of the star that was, and it now begins its own strange and extraordinary existence. The chaos of the supernova fades, and what remains is eerily calm. The newborn neutron star sits in silence amid the wreckage of the exploded giant. There is no roaring fire burning in its core any longer, no bright stellar furnace, just a dense, hot ball of matter slowly cooling in the dark. In that quiet aftermath, the neutron star is utterly unlike the star it came from. All the tumult of fusion and radiation is over. What's left is a small, incredibly dense sphere governed by gravity and quantum forces alone. This neutron star is composed of matter in an extraordinary form. Nearly all the protons and electrons that once made up atoms have been fused into neutrons. Atoms, as we know them, cannot survive here. The pressure is far too great. Instead of a collection of separate atoms with empty space between, the material of a neutron star blurs together into one immense ocean of subatomic particles. You can imagine it as a single giant atomic nucleus, about 20 kilometers across. It is as if an entire star's worth of matter has been compacted into a nucleus-sized volume, but scaled up to city dimensions. In fact, in these depths, there is almost no distinction between one atomic nucleus and the next. Everything touches, packed solid by gravity's relentless squeeze. Without heat or fusion pushing outward, what stops this stellar core from collapsing further? The answer lies in the strange quantum rules that govern the neutrons. Neutrons, like electrons, obey the Pauli exclusion principle. No two identical neutrons can occupy the same quantum state at the same time. When neutrons are pressed too closely, they begin to resist fiercely, simply because quantum mechanics forbids them from crowding any tighter. This resistance is called neutron degeneracy pressure, and it provides a powerful outward push. It is akin to the electron degeneracy pressure that held up a white dwarf, but vastly stronger. Where electrons once whispered, neutrons now speak with a firm, quiet authority, bracing the star against further collapse. Yet neutron pressure alone is not the full story. At these extreme densities, another force steps in, the strong nuclear force, which ordinarily binds protons and neutrons inside atomic nuclei. In the confined heart of a neutron star, the neutrons are packed so closely that they feel each other's presence intensely. The strong force has a complex personality. It is powerfully attractive at moderate distances, but when particles are forced nearly on top of each other, it turns repulsive. In this tiny star, neutrons are pushed to just such extreme closeness. They jostle one another with immense force, and the strong force responds by pushing back. This provides an additional, stiff resistance deep in the core, beyond what degeneracy alone can supply. It is a quiet strength. There is no explosion or sound, just an unyielding solidity that comes from the fundamental forces of nature. The mighty pull of gravity is held at bay by the combined quantum pressure of neutrons and the silent, implacable repulsion of the strong nuclear force. The result is an object so dense and compact it defies imagination. A single teaspoon of neutron star material would outweigh a mountain. In more concrete terms, a sugar cube-sized lump of this matter could contain as much mass as all of humanity, or even more. The density deep inside reaches hundreds of millions of tons in each cubic centimeter. Such figures are almost impossible to picture. One way to sense it is this. If you could stand on the surface of a neutron star, an impossible feat, gravity would hold you down with crushing might. Your body would weigh billions of times more than it does on Earth. If you dropped a pebble from waist height, it would slam into the ground in microseconds, released in a flash of energy, having fallen only a meter, but accelerated to tremendous speed by the intense gravity. Everything about the neutron star is extreme, yet on the outside it appears deceptively unassuming. Just a small, dark sphere slowly cooling in space. No raging fire burns on its surface. Any light it emits now comes from residual heat or other subtle processes. In the aftermath of its violent birth, the neutron star has entered a phase of deep quiet. Inside, quantum pressures and nuclear forces hold chaos at bay. Outside, the star shines only softly, if at all, as it radiates away the last heat of its formation. Matter has been squeezed to silence, crushed into a form where atoms have vanished, and even light itself struggles to escape the star's immense gravity. This silence is not emptiness. It is the hush of a million triumphs of pressure over collapse. It is a balanced stillness that will endure for ages, as the neutron star slowly cools and rotates in the darkness. Beneath the neutron star's placid surface lies a remarkable layered world. The star is only a few tens of kilometers across, yet it has distinct regions from its thin crust down to its mysterious core. The outermost layer, the crust, is essentially a gigantic crystal of atomic nuclei. Immense gravity has frozen the star's exterior solid, despite the intense heat inside. Atoms on the surface are crushed so tightly together that they arrange into an orderly lattice, making the crust incredibly hard and strong. In fact, this may be the strongest material in the universe. Iron and other nuclei sit locked in place, forming a shell of matter as rigid as diamond, but far denser. If you could tap on it, the neutron star's crust would ring like a solid bell, albeit one at incomprehensibly high pitch, testifying to its stiffness. This solid crust is comparatively thin, only a kilometer or two deep, a razor-thin rind around the star's immense bulk. As one moves inward, the pressure and density climb even higher. Within the deeper layers of the crust, the nature of matter begins to change. Nuclei become increasingly unstable under the crushing weight. They capture electrons and swell with neutrons, growing into exotic heavy elements. Eventually, so many neutrons are packed in that some can no longer be contained inside nuclei. They leak out, forming a free-floating sea of neutrons between the nuclei. The solid lattice persists, but it is now bathed in a drenching tide of neutrons that drip out from the nuclei, like water from a saturated sponge. This inner crust is a bizarre amalgam of solid and liquid, rigid ion cores and a super-dense neutron fluid coexisting. Deeper still, at the very base of the crust, the distinction between nuclei and neutron sea nearly vanishes. The forces between particles compete in strange ways here. Protons and neutrons inside nuclei begin to arrange themselves into unusual shapes as they jostle for space. Instead of isolated spherical nuclei, matter may organize into long cylinders or broad, flat sheets of nuclear matter. Scientists have whimsically nicknamed these configurations nuclear pasta, as they resemble spaghetti strands and lasagna layers on the microscopic scale. It is a playful name for a profound state of matter. These tangled nuclear structures make the crust astonishingly resilient. This deepest crust, laced with nuclear spaghetti and permeated by super-dense neutron liquid, represents the final barrier between the star's outer shell and its core. Crossing that boundary, one enters the core, the inner bulk of the neutron star, extending perhaps 10 kilometers across. Here, the last vestiges of ordinary atomic structure melt away entirely. There are no more crystal lattices or isolated nuclei, no more empty space between particles. The core is a fluid, a single colossal mass of neutrons mixed with a smaller number of protons and electrons. Imagine an ocean of neutrons, so dense that a single drop contains more mass than a mountain. This neutron fluid is not like any normal liquid. It is a quantum superfluid. Below a certain critical temperature, the neutrons pair up in a delicate quantum dance, flowing without friction. Within the star's core, trillions of tons of neutron fluid can glide and swirl with perfect freedom, never grinding to a halt. This superfluidity means that rotational motion in the core takes on an eerie, organized form. The fluid rotates by forming an array of invisible quantum whirlpools, tiny vortices threading through the neutrons like fine, evenly spaced fibers. These vortex lines spin along with the star, and together they let the superfluid interior turn almost without friction under the crust. Alongside the neutrons, a small fraction of protons also moves through the core. These protons, though few, carry positive charge and thus feel the electromagnetic force. They too are squeezed into a quantum pairing state, a superconducting state. In this state, electrical resistance vanishes and currents can flow forever without fading. The star's powerful magnetic field, generated when it was born, is trapped within this superconducting core. But it cannot move freely through a perfect conductor. Instead, the magnetic field is confined into thin, tube-like structures penetrating the core, quantized flux tubes of magnetism. These tubes are whisper-thin and tremendously long, stretching through the core like threads of an invisible fabric. Each thread carries an immense magnetic tension, yet they are locked in place within the superconductor. In essence, the neutron star's core contains a hidden lattice of magnetic needles, a forest of field lines pinned in the dense matter. All of these layers and elements, the rigid crystalline crust, the superfluid neutron rivers in the inner crust and core, and the superconducting magnetic threads, coexist in a delicate harmony. The crust supports the tremendous weight of the star above it, while the superfluid interior allows the star to rotate and adjust without tearing itself apart. The thin magnetic flux threads link the core to the crust, anchoring the star's magnetic field and connecting the inside to the space around it. Through this complex structure, the neutron star remains an integrated whole, threaded throughout with forces of quantum physics. It is as if the star carries within it an entire hidden landscape. There are crystalline plains, liquid seas, and taut magnetic harp strings, all concealed beneath an unassuming surface of cooling neutron matter. For now, these exotic inner structures remain entirely hidden from direct sight. We infer their existence from theory and subtle clues, as no telescope can peer into a neutron star's heart. But even without seeing them, we know they must be there to explain how the star behaves. In the stillness of the neutron star's exterior, the crust and core quietly do their work, conducting electricity, flowing with superfluid grace and bracing against gravity's crush. This intricate interior, so calm and organized, sets the stage for the neutron star's more noticeable phenomena. The next act of our journey will witness how this deeply ordered structure gives rise to extraordinary cosmic beacons, turning some neutron stars into lighthouses that sweep the void with cosmic light. Far out in the cosmic dark, a tiny star shines as a steady, rhythmic beacon. Against the black sea of space, its light flashes on and off with uncanny precision. This is a spinning neutron star, broadcasting its presence, a pulsar. With each turn, it sweeps a beam of energy across the void, much like a lighthouse sweeping its beam over a dark ocean. From Earth, we perceive those sweeps as pulses of light or radio waves, arriving in a regular cadence, like the ticking of a celestial clock. A pulsar is born from the aftermath of a supernova, inheriting the neutron star's rapid rotation and strong magnetic field. Imagine the neutron star as a cosmic flywheel, spinning dozens or even hundreds of times each second. As it spins, its intense magnetic field whips around, accelerating charged particles near the magnetic poles to incredible speeds. These particles emit focused beams of electromagnetic radiation, often radio waves, that stream out along the magnetic poles. If the star's magnetic poles are not aligned with its axis of rotation, the beams swing around as the star rotates, carving vast circles through space. Any distant observer along the path of those beams will see a flash of emission each time one of the beams points their way. To an astronomer with a radio telescope, the signal from a pulsar is unmistakable. A series of blips or ticks, timed so evenly that they rival the steadiness of the finest clocks. The pulses can range from seconds apart to mere milliseconds apart, depending on how fast the neutron star is spinning. In between pulses, the star is almost perfectly silent. Then, right on cue, another burst arrives. The regularity is astonishing. Early in their discovery, these rhythmic signals were so unexpected that the first pulsar was jokingly labelled LGM1 for Little Green Men. But it was soon understood that the source was even more extraordinary. A rapidly spinning neutron star, turning on its axis and flashing its polarized light across the galaxy. Each pulse is like a heartbeat in the darkness, a brief moment of energy, followed by a longer pause. Picture sitting on a lonely shore at night, watching a distant lighthouse out at sea. Every few seconds, a brief flash, then darkness, then the flash again. This is how a pulsar announces itself to the universe. The neutron star's rotation is so stable that those flashes arrive as predictably as a metronome. Some pulsars repeat with metronomic perfection thousands of times per minute, while others spin more slowly, but all of them gradually slow down over long timescales. The light from a pulsar is usually not visible to human eyes. Most pulsars shine mainly in radio waves or high-energy light like X-rays. Yet a few rare pulsars, like the one at the heart of the Crab Nebula, emit pulses across the spectrum, including visible light. In each case, what we see or detect is the effect of the star's magnetic poles sweeping past our line of sight. We happen to be in just the right spot to catch the beacon as it swings by. If we were elsewhere in the galaxy, most pulsars would be invisible. Their beams would sweep past without ever pointing our way. But from our particular vantage, we have catalogued hundreds of these cosmic lighthouses, each with its own unique rhythm. The precision of pulsar timing is one of the wonders of nature. Some pulsars keep time better than the rotation of the Earth, or the ticks of an atomic clock. A pulsar's steady beat can be used by astronomers to study everything from interstellar space to the behavior of ultra-dense matter. When you listen to a recording of a pulsar's signals converted to sound, it can sound like a steady drum, or a rapid hum, or even a high musical note, depending on its spin rate. It is the sound of a star's rotation, scaled into the range of human hearing, a stellar heartbeat echoing across space. These neutron star lighthouses do more than captivate our imagination. They also serve as cosmic laboratories. With each rotation, a pulsar gradually expends a tiny bit of its energy, radiating it away in those beams. Over millions of years, the pulsar will slow its spin, its flashes coming more and more gently. But while it flashes, it provides a regular beacon we can measure and study. Pulsars have taught us how neutron stars are structured and how gravity and magnetism behave under extreme conditions. And they are useful too. Navigation systems have even been proposed that use pulsars like GPS satellites, since their positions and timings are so reliable. In the silent expanse of space, a pulsar's blinking might seem like a faint, lonely signal, but to anyone tuned in, it is a marvel of consistency and power. Each pulse is a reminder of the neutron star's existence, a distant, dense, city-sized star spinning in darkness and announcing, "I am here," with every turn. These cosmic lighthouses are perhaps the most striking way a neutron star makes itself known, by turning its deadly magnetic might and rapid rotation into a gentle, celestial heartbeat that can be detected across the galaxy. In the next moments, we will see how these spinning stars, though steady, are not unchanging. Their rhythms can evolve and even hiccup, revealing the dynamic life hidden beneath their clock-like facade. Neutron stars may spin with clock-like steadiness, but even clocks wind down. Every pulsar is gradually losing the energy of its rotation, a slow deceleration that acts like a gentle brake on the spinning star. With each passing year, the pulsar's rotation grows imperceptibly slower. The change is so slight that decades might pass before the difference could be noticed without precise instruments. Yet over millennia, these tiny losses accumulate. The star's once whirling pace eases into a more sedate rhythm as it ages. This steady spin down is the rhythmic loss of youth, the pulsar's gradual slide into old age as its energy is siphoned away by its shining beams. This breaking of the star is not due to any physical touch or conventional friction. Instead, the pulsar's own magnetic fields and winds carry off its rotational energy. As the magnetic field sweeps through space, it acts like a dynamo, generating electromagnetic radiation and driving a flow of charged particles away from the star. This constant emission of energy and particles saps the pulsar's spin ever so slightly. It is as if the lighthouse's beam itself drags on the rotation, a barely perceptible resistance that, over long times, slows the beacon's turning. The pulsar, shining its light into the cosmos, pays for that brilliance with a tiny fraction of its spin. Usually, this slowdown is smooth and predictable, a gradual lengthening of the pulsar's period. But every now and then, something strange interrupts the steady rhythm. A pulsar will suddenly speed up for a moment, its rotation rate jumping slightly higher. To an astronomer listening to the pulses, it's as if the ticking star skipped a beat or quickened its tempo out of turn. These sudden increases in spin rate are known as glitches. They are slight, often a change of 1 part in a million or less, but unmistakable against the regular background of the pulsar's slowing. One pulse arrives a tiny bit earlier than expected, and from that moment on, all subsequent pulses are just that little bit faster than before. What could make a spinning star abruptly spin faster? The answer lies deep inside the neutron star's hidden interior. Recall that the crust is solid, while the inner core contains a superfluid of neutrons. Under normal conditions, the crust and superfluid rotate together in lockstep. But as the pulsar slows, the superfluid inside, which can rotate in discrete vortex lines, might lag slightly behind or store some extra angular momentum. A glitch may occur when the superfluid suddenly hands some of that stored momentum back to the crust. In an instant, the crust's rotation speeds up, trying to catch up with the superfluid within. Another possibility is a starquake. As the neutron star's spin slows over years, its solid crust might gradually deform and then crack, adjusting the star's shape. In the brief moment of that quake, the star's rotation can change abruptly. In either case, a shift in the superfluid's grip or a quake in the crust, the result is a sudden, small acceleration of the star's spin. These glitches are like quiet heartbeats in the life of a pulsar, rare and subtle signals of the star's inner life. A pulsar might spin unwaveringly for years or decades. Then without warning, it hiccups, as if something deep inside gave a push. After a glitch, the steady braking resumes anew. The pulsar continues its age-long slowdown, now starting from a slightly higher spin rate. Sometimes, astronomers see the star's rotation relax back toward its previous rate over weeks or months, hinting that internal adjustments are settling. In other cases, the pulsar simply establishes a new, slightly faster baseline and carries on ticking down from there. Each glitch reminds us that beneath the rigid crust and the precise pulses, the neutron star is a dynamic object. Superfluids swirl and stresses build and release in its depths. Over centuries and millennia, the cumulative effect of the pulsar's braking is significant. A young pulsar born spinning dozens of times a second may, after millions of years, spin only a few times a second, or even slower. As the pulsar loses rotational energy, its beams weaken and can eventually flicker out. In its old age, the neutron star may become too slow and faint to detect, joining the countless quiet stellar remnants that drift through the galaxy unseen. The rhythm of loss, this gradual fading of a pulsar's spin and energy, is the natural final movement of the neutron star's life as an active beacon. Yet, even in this slow decline, the pulsar continues to teach us. By monitoring the spin-down rates and sudden glitches, scientists glean clues about the star's composition and the forces at play within. Each tiny change in rotation is like a note in a hidden song of the star's interior, hinting at superfluid behavior, crustal strength, and magnetic stress. The pulsar's steady aging, marked by its lengthening period, and its occasional heartbeats of change, marked by glitches, together compose a story of a star gradually coming to rest. From the outside, we see only the timing of the flashes, but those timings carry the signatures of fundamental physics. These subtle clues compel us to probe deeper, to test our understanding of matter under such extreme conditions. To do that, we must find ways to measure the unmeasurable, to weigh and size up neutron stars from afar. In the next part of our journey, we will discover how astronomers accomplish this, revealing what makes these remarkable stars possible. How do you take the measure of an object so remote and strange as a neutron star? We cannot set one on a scale or slide a measuring tape around its middle. Instead, astronomers rely on nature's own tools and some creative ingenuity to weigh and size up these unseen giants. The key lies in observing how neutron stars affect their surroundings and the signals they emit. By carefully watching the dance of a neutron star with a companion or the timing of its light, we can tease out clues to its mass and radius. the basic traits that define its physical character. One of the most straightforward ways to weigh a neutron star is to observe it in a binary system, orbiting another star. In such cosmic pairs, gravity tugs both objects around a shared center. By tracking the motions, how fast the stars orbit, and how far apart they are, scientists can calculate the masses of the stars involved. A neutron star's intense gravity can also reveal itself through more subtle means. For instance, if the neutron star is orbiting with a companion and passing in front of it from our perspective, the neutron star's gravity bends and delays the companion's light ever so slightly. This effect, known as a Shapiro delay, can be measured with precise timing and used to infer the neutron star's mass. Through observations like these, we have learned that many neutron stars cluster around 1.4 times the mass of the Sun. A few push far beyond, up to 2 times the Sun's mass or more. Measuring a neutron star's size, its radius, is a tougher challenge. These stars are only about 20 kilometers across, and so distant that they appear as points of light. Direct imaging of a neutron star's surface is impossible with current technology. Instead, astronomers use indirect clues. One approach involves looking at neutron stars that emit pulsing X-rays, especially those in close binaries that accumulate hotspots on their surfaces. As the star rotates and these hotspots spin in and out of view, the X-ray brightness changes in a regular pattern. By analyzing the details of that pattern, how quickly it rises and falls, how the light is distorted, scientists can estimate the star's size. The gravity of the neutron star is so strong that it warps the path of light near its surface. Light emitted from the far side of the star can be bent enough to reach our telescopes. By measuring such effects, we can deduce how compact the star must be. The result of these careful studies suggests that a typical neutron star spans roughly 20 to 25 kilometers in diameter. In other words, a neutron star is about the size of a city, even though it weighs more than the Sun. With mass and radius in hand, we can probe the essence of neutron star matter. These two numbers, how heavy the star is and how tightly that mass is packed, are the keys to unlocking the equation of state, the relation between pressure and density in the star's ultra-dense core. Imagine squeezing a material. A soft material compresses easily, resulting in a smaller object for a given mass, whereas a stiff material resists compression, yielding a larger size. Neutron star matter can be soft or stiff, depending on its internal physics. If we find a neutron star that is more massive than expected, yet not overly large, it tells us the matter inside must provide tremendous pressure, perhaps through exotic particle interactions, to support that mass, a stiff equation of state. Conversely, a smaller than expected star of a given mass might indicate a softer equation of state, meaning the matter compresses more readily. Each new measurement of a neutron star's mass and radius narrows down the possibilities for matter at nuclear densities. We are inching closer to the true equation of state. So far, nature has shown us neutron stars of up to a bit above 2 solar masses. The record holder weighs in around 2.3 times the mass of the Sun, astonishingly heavy for such a small sphere. This pushes right up to the boundary of what neutron star matter can support. The existence of such a massive neutron star tells us that the matter in its core must be extremely stiff, otherwise it would have collapsed further into a black hole. Scientists suspect there is a fundamental limit, a precise point of no return. The Tolman-Oppenheimer-Volkoff limit, beyond which no neutron star can remain intact. If an object's mass exceeds this limit, perhaps around 2.5 to 3.0 times the Sun's mass, according to current estimates. Gravity's grip will overwhelm all internal pressures, and the star will collapse into a black hole. This final mass limit is the ultimate calm frontier for neutron star physics. Once it is crossed, the story of matter in the star comes to an end, leaving only a hidden singularity behind an event horizon. We have not yet observed a neutron star surpassing that limit. Nature seems to quietly transform those cases into black holes without fanfare. But the concept of this limit gives us a sense of closure, an understanding that even the strange solidity of neutron star matter has its breaking point. Every measurement of a hefty neutron star edges us closer to pinpointing that boundary. And as we weigh and measure these cosmic remnants, we are also testing the very laws of physics under conditions impossible to reproduce on Earth. Each new data point, a mass here, a radius there, helps sketch the outline of an equation of state that dictates the neutron star's being. Despite great strides, there remain uncertainties. Neutron star cores might harbour surprises. The appearance of exotic particles like hyperons, or a transition to free quark matter at extreme density. These would subtly alter the softness or stiffness of the star. Our current measurements hint that many neutron stars share similar radii, which suggests a delicate balance in their internal physics. As instruments improve and new observations roll in, including gravitational waves from colliding neutron stars, which carry an imprint of their deformability, we expect to sharpen the picture further. Weighing the unseen and sizing the invisible have turned neutron stars into profound tools for physics. By figuring out how heavy and how large they are, we confront the behavior of matter at densities beyond an atomic nucleus. In the next part, we will shift focus from the weight and pressure of these stars to another domain of their story, the faint warmth that lingers on their surfaces. Even as they seem cold and dark from afar, neutron stars glow with a residual heat that whispers of their fiery birth and internal mysteries. Neutron stars are often thought of as cold, burnt-out cores, and indeed they no longer produce energy through fusion. But that does not mean they are truly cold. In the aftermath of its violent birth, a neutron star is searingly hot. Its surface temperature can exceed 1,000,000 degrees in the first 1,000 years. Even as it cools over time, it retains a thermal glow. We call it cold only in comparison to the blazing furnace of a normal star. In reality, a neutron star continues to radiate a faint heat from its surface, a ghostly afterglow of its earlier inferno. This thermal emission from a neutron star is usually feeble and easy to overlook beside the star's intense, magnetic-powered phenomena. Yet with sensitive instruments, we can detect it. The glow is typically brightest in X-rays and far ultraviolet, corresponding to temperatures of a few 100,000 to a few million kelvins. If you could see a neutron star up close, it might look like a dull red ember or a tiny blue-white sphere, depending on its age. Not brilliant like the sun, but gently aglow against the blackness of space. As the star ages and cools, its light shifts towards softer, lower energy wavelengths. Astronomers studying isolated neutron stars, those without pulsing radio beacons or binary companions, have found several that shine primarily with this soft thermal glow. These cosmic cooling embers allow us to take the temperature of a neutron star's surface directly. For example, one nearby isolated neutron star has a surface temperature of only a few 100,000 kelvins. Dim in absolute terms, yet still far hotter than any planet. One intriguing feature of neutron star heat is that it is not always evenly distributed. While the overall surface might be hot, certain regions can be even hotter. In many pulsars, for instance, The areas around the magnetic poles are warmer than the rest of the crust. These hotspots are created by energetic particles funneled by the star's magnetic field, crashing into the surface near the poles. Imagine the magnetic field lines as invisible rails guiding showers of electrons and ions down onto specific patches of the crust. The impact heats those patches extra bright. As a result, a pulsar can have two small, hot circles on opposite sides of its globe, glowing cap regions that emit more X-rays than the surrounding surface. When the neutron star rotates, these hotspots sweep in and out of view, adding a faint modulation to the star's X-ray output, much like a lighthouse whose lamp has a pair of brighter panels. By studying the spectrum of the neutron star's thermal radiation, essentially how its brightness varies with X-ray energy, scientists can learn about conditions on the surface. The emitted light bears imprints of the star's gravity and composition. For example, the intense gravity redshifts the radiation, stretching it to slightly lower energies. This effect must be accounted for when deducing the temperature. Additionally, if the neutron star has a thin atmosphere, perhaps a few centimeters of hydrogen or helium that survived or accumulated, that atmosphere can tweak the spectrum by absorbing certain energies and letting others through. Most observed isolated neutron stars show an X-ray spectrum that is soft, meaning it peaks at relatively low X-ray energies. It closely matches what we expect from a hot, bare surface, or one with a very thin atmosphere. It is essentially the spectrum of a thermal blackbody. Only subtle distortions from gravity and surface composition differentiate it from an ideal one. The notion of a neutron star as a small, dense world is fitting when we consider its surface. Unlike a black hole, a neutron star has a solid, or at least liquid surface that one could, in principle, touch or walk on, ignoring the lethal gravity. This surface can have weather of a sort, particle bombardment at the poles, starquakes in the crust, and a gradual cooling over eons. The star's crust, made of atomic nuclei packed in a crystal, holds in the immense heat of the interior and releases it slowly into space. Over 1 million years or so, a neutron star's surface might cool from 1 million degrees down to a few 100,000. After 10 million years, it may only glow faintly in X-rays, and beyond that, it could become nearly impossible to detect. Yet even at those advanced ages, if we could measure it, some warmth would remain. It would be a faint whisper of the star's fiery birth, throbbing beneath the cold. Such an ancient neutron star would be exceedingly difficult to spot against the backdrop of space. Observations of thermal radiation from neutron stars provide yet another window into their physics. By comparing the observed temperatures and cooling rates to theoretical models, astronomers can infer internal processes at work. Certain rapid cooling behaviors might indicate the onset of superfluidity in the core, which opens new channels for neutrino emission and thus faster cooling. An unexpectedly warm older neutron star might hint at ongoing energy sources inside, such as friction from superfluid vortices or decay of a strong magnetic field heating the crust. Magnetars, with their ultra-strong magnetic fields, exhibit surface temperatures and X-ray output higher than a normal pulsar of the same age, because their magnetic fields twist and dissipate energy as heat. In the soft glow of a cooling neutron star, we thus find subtle clues to its inner workings. These clues complement the information gained from pulsar timing and mass measurements, rounding out the story of the neutron star's life cycle. We see a once fiery star ember settling into twilight, its surface cooling but never instantly going dark, instead fading gradually. This gentle fading light is a testament to the neutron star's residual heat, a final gift of warmth that lingers long after its more dramatic fireworks have ceased. In our next part, we will explore the extremes that lie at the outskirts of neutron star behavior. Those rare cases where magnetism, spin, and accretion push these stars to their limits, bridging the gap to even stranger phenomena. Not all neutron stars live out their lives in quiet rotation and gradual cooling. A select few tread the edges of what is physically possible, pointing the way to even stranger phenomena. Among these are the magnetars, neutron stars endowed with magnetic fields hundreds of times stronger than the typical pulsar. Most of the time, a magnetar appears unassuming, but its magnetic stress can build until, in a sudden moment, the crust shifts and a burst of energy is released. What might be a slight twitch in the star sends out an intense flare of X-rays and gamma rays, momentarily making the magnetar briefly extremely bright. These events are rare and brief, but they show the neutron star in a new light, not as a steady beacon, but as a slumbering dragon capable of sudden outbursts. There are also neutron stars that spin at the very brink of breakup. Millisecond pulsars, as they are called, rotate hundreds of times each second, their surface moving at a significant fraction of the speed of light. Such incredible spin rates are believed to be achieved when an aging neutron star siphons gas from a companion in a binary system. The infalling matter transfers its orbital momentum to the neutron star, whipping it into a faster and faster spin. In essence, the old pulsar is recycled into a millisecond pulsar, a fantastically precise clock that can rival atomic clocks in stability. These millisecond pulsars represent the extreme of rotation, showing how fast a neutron star can twirl without flying apart. Then there are the so-called hungry neutron stars in close binaries, which actively feed on their companions. In these systems, the neutron star's intense gravity pulls gas from a nearby normal star, creating an accretion disk of hot plasma. As this gas falls onto the neutron star's surface, it releases a torrent of X-rays and occasionally triggers thermonuclear flashes across the star's surface. Such X-ray binary systems can be tumultuous. The neutron star may alternate between quiet and eruptive phases, and over time, the accretion of mass can spin it up or push it toward the limits of stability. In some cases, two neutron stars in a tight dance may eventually spiral together and merge, unleashing gravitational waves and forging heavy elements in one last flash of glory. Each of these extreme scenarios, the magnetar's magnetic fury, the millisecond pulsar's frenetic spin, the accreting neutron star's ravenous appetite, stretches the neutron star phenomenon to its limits. They are the exceptions that help prove the rule, illuminating the full range of possibilities for matter under extreme conditions. Through them, we see neutron stars not just as static spheres, but as dynamic objects that can be pushed to astonishing behaviors. This gentle exploration has taken us from the serene rotation of ordinary pulsars to the threshold of something even more exotic. As we move forward into the next part of our journey, we will step fully into these extremes, where the boundary between neutron stars and the next stage of cosmic mystery comes into view.